In the freezing dark beyond Neptune, the orbits of icy worlds are tilting 15 degrees out of line. Something is pulling on them, something we can't see. A planet smaller than Earth, hiding twice as far from the Sun as Pluto. A cliff in space where objects vanish without warning. Worlds that should not exist on orbits no known force can explain. If this story pulls you in, hit that like and subscribe so you don't miss what comes next. Tonight we follow the gravity. We find the ghost. Prepare yourselves. We begin. Past the orbit of Neptune, the solar system goes dark. The sunlight here is 1,000 times weaker than what reaches Earth. Temperatures hover near -400 degrees Fahrenheit, and drifting through this frozen wasteland is a ring of icy worlds wider than the orbit of every planet combined. Astronomers call it the Kuiper belt. Picture a vast donut of debris circling the Sunday. It starts just past Neptune and extends to roughly 1,000 times the Earth-Sun distance. Inside this ring float hundreds of thousands of icy bodies larger than 60 miles across. Some carry frozen methane, some carry ammonia, some carry water older than the planets themselves. Pluto lives here, so does Eris, so does a strange, peanut-shaped world called Arakoth that the New Horizons spacecraft flew past in 2019. These are the leftovers. The crumbs from when our solar system was being built 4.5 billion years ago. But something about this graveyard of ice is wrong. The objects out here are not moving the way physics says they should. Some of them swing on orbits so elongated they look like comets. Some are tilted sideways. Some are detached entirely from the gravity of every known planet. And the deeper astronomers look, the stranger the patterns become. For years, scientists assumed the Kuiper belt was a quiet museum, a place where nothing changed, a place where ancient ice waited in the dark for someone to find it. That assumption is collapsing right now. In the last 3 years, telescopes in Hawaii, Japan, and Chile have started revealing something hidden inside the data. The numbers do not add up. The orbits do not line up. Entire populations of objects appear to be responding to a gravitational pull from something we have never seen. Think of the Kuiper belt like a lake on a still morning. The surface should be flat, the water should be calm, but astronomers are now seeing ripples, long, slow waves crossing the ice. And ripples only happen when something disturbs the water. So the question becomes simple. What is disturbing the lake? A team at Princeton University released a paper in August of 2025 that shook the astronomy community. They had analyzed the orbits of more than 150 Kuiper belt objects. Beyond a certain distance, the entire population was tilted by about 15 degrees relative to the rest of the solar system. 15 degrees does not sound like much, but on the scale of the outer solar system, it is enormous. It is the gravitational signature of a body large enough to bend the orbits of countless worlds at once. A body that, if it exists, has been pulling on this ring of ice for billions of years. And here is the part that makes scientists nervous. Their simulations suggest the warp should have faded by now. Any explanation that does not involve an actual planet falls apart. A passing star would have left a signal that decayed long ago. A leftover from the solar system's birth would have smoothed out. Something is keeping the warp alive. Something that is still out there, still pulling, right now. And the deeper into the belt we look, the more wrong things become. Because the warp is only the first clue. The next discovery is a cliff. A wall in space where everything just stops. Imagine spinning a plate of marbles. They roll outward in a flat ring, all moving in the same plane, all obeying the same simple physics. That is how the solar system should look from above. 8 planets, all orbiting in a roughly flat disk. The Kuiper belt extending that disk outward, following the same tilt, the same plane, the same direction. For the first 50 astronomical units past the Sun, that is exactly what we see. Pluto and its neighbors trace orbits more or less aligned with Earth, Jupiter, and Neptune. The disk holds, the math works, Then you reach 80 astronomical units. That is roughly 8 times the distance from the Sun to Saturn, so far out that sunlight takes more than 10 hours to reach you. And at this distance, the disk does something it has no right to do. It tilts. Researchers analyzed the orbits of more than 150 Kuiper belt objects. Beyond Neptune's gravitational influence, they examined objects between 50 and 80 astronomical units, and those largely followed the plane of our solar system. But when they looked at objects orbiting the Sun between 80 and 200 astronomical units, they found their paths were warped by about 15 degrees. Picture our solar system like a flat dinner plate. Now imagine grabbing the outer edge of that plate and bending it upward. That is what the Kuiper belt is doing beyond 80 AU. It is curving away from the plane the inner planets follow, as if some invisible hand is lifting the rim. This is a confirmed finding, published in a peer-reviewed paper in the monthly notices of the Royal Astronomical Society in August of 2025. The lead author, an astrophysicist named Amir Siraj at Princeton, did not jump to conclusions. He and his team spent months trying to explain the tilt with anything other than a hidden planet. They tried passing stars. A nearby star skimming through the outer solar system millions of years ago could have nudged objects into tilted orbits. But the simulations showed something brutal. Any tilt caused by a stellar flyby would have smoothed back out long ago. The rest of the solar system would have erased the signal. They tried the formation of the solar system itself. Maybe the disk was always slightly warped, a leftover scar from the chaos of planet building. But the math killed that idea too. A primordial warp would have decayed across 4.5 billion years. The tilt is still there, today, right now, which means something is actively maintaining it. That is the punch in the gut. A warp this clean, this persistent, can only survive if a real, physical, gravitating object is constantly pulling on the belt. It was quite a surprise to find that beyond about 80 times the Earth-Sun distance, the solar system suddenly appears to be tilted by about 15 degrees. And this is what sparked the Planet Y hypothesis, Siraj said. Think of a sleeping person under a blanket. If you see the blanket bulging upward and staying that way, there has to be something holding it up. The bulge cannot exist on its own. The Kuiper belt is the blanket. The bulge is real, and whatever is underneath has been there long enough to leave a permanent print on the solar system. The team estimates the odds of this warp being a statistical fluke at 2 to 4%. Those are not certainty odds. But early evidence for Planet 9, almost a decade ago, came in at similar numbers. Hidden planets do not announce themselves. They whisper through the data, and this whisper is loud enough that researchers now have a name for whatever is responsible. They call it Planet Y, a hidden world we have never photographed, a world smaller than Earth, a world that might be closer than we ever guessed. What kind of object has the gravity to bend a belt this large, but the stealth to stay invisible for centuries of telescope work? That is the next clue. The suspect has a profile now. Astronomers can describe it without ever having seen it. It is bigger than Mercury, smaller than Earth. It orbits the Sun somewhere between 100 and 200 times farther out than our planet does. Its orbit is tilted at least 10 degrees from the plane the other planets follow. And it has been there, quietly tugging on the Kuiper belt for most of the solar system's history. This is Planet Y. Planet Y is most likely a Mercury to Earth mass body, approximately 100 to 200 times the Earth-Sun distance, tilted at least 10 degrees relative to the other planets. Siraj told reporters in October of 2025. Stop for a moment and consider what that means. A planet, perhaps the size of Mars, perhaps slightly larger, orbiting in our solar system, a world with its own gravity, its own day, its own seasons. A world that almost certainly has a frozen surface, possibly with mountains, possibly with ice volcanoes, possibly with a thin atmosphere of nitrogen and methane, and we have never seen it. Not in the 400 years since the invention of the telescope, not in the 70 years of modern radio astronomy, not in the decades of infrared sky surveys. Planet Y, if it exists, has stayed hidden because of three brutal facts. First, it is far. At 150 times the Earth-Sun distance, sunlight reaching its surface is more than 20,000 times weaker than what we feel on Earth. There is barely any light to reflect back to us. Second, it is small. A body smaller than Earth has a tiny surface area compared to Neptune or Uranus. Less area means less reflected light. From our vantage point, it would appear as a faint smudge moving across the sky so slowly that you could watch it for a year and barely notice motion. Third, it is in the wrong place. Astronomers have searched the obvious regions, the ecliptic, the plane where all the known planets orbit, but Planet Y is tilted. It spends most of its time outside that plane, drifting through a part of the sky where no one expected a planet to be. This is why a Mercury-class world could go unnoticed for so long. It is hiding above the deck. Here is what makes Planet Y different from older hypotheses. Earlier theories about hidden planets focused on something enormous. Planet 9, proposed back in 2016, was supposed to be 5 to 10 times the mass of Earth. A super-Earth, a monster compared to what Siraj is now proposing. Planet Y is a different kind of suspect. It is small enough to have escaped detection, close enough to actively warp the inner Kuiper belt, plausible enough to fit the data without breaking any laws of orbital mechanics. This paper is not a discovery of a planet, but it's certainly the discovery of a puzzle for which a planet is a likely solution, Siraj said. And here is the strange wrinkle. Planet Y does not rule out Planet 9. Both could exist. One closer, one farther, one smaller, one larger. Two hidden worlds in the same dark backyard, each pulling on different layers of the Kuiper belt. A research fellow named Xiangyu Wang in Taiwan independently called the Planet Y idea plausible. He noted that simulations keep failing to remove the need for an actual planet. The warp simply will not go away without one. Picture a detective standing over a crime scene. Footprints in the snow, no suspect in sight. The footprints are too fresh to belong to someone who left hours ago. Someone is still here, still walking, still leaving marks. That is where we are. The footprints are real. The walker is somewhere in the dark, but Planet Y is not the only intruder. Because something else, much farther out, is doing something even stranger. It is detaching worlds from the solar system itself. A warp in the Kuiper belt is not just a frozen photograph. It is a moving signal, and that movement is the key to everything. Gravity in space behaves like a memory that fades. Every disturbance, every push, every nudge gets smoothed out over time by the relentless tug of the larger objects nearby. The Sun, Jupiter, Saturn, Neptune. Together they act like a gravitational sandblaster, slowly erasing any tilt or distortion that does not have a constant source. That is why Siraj's team spent so much time trying to kill their own hypothesis. They wanted the warp to be ancient. They wanted a clean, simple, no planet needed explanation. Because adding a new planet to the solar system is a big claim, bigger than nearly any claim in modern astronomy. They started with the most obvious culprit, a passing star. Stars do drift past our solar system occasionally. About 70,000 years ago, a small red dwarf called Schultz's star came within 1 light year of the Sunday closer than any star is right now. Some scientists believe its gravity may have sent comets tumbling into the inner solar system. So, the team modeled what a flyby would do to the Kuiper belt. The answer was clear. A passing star could tilt the belt for a while, maybe a billion years. But then the solar system would slowly smooth the disturbance away. The orbits would relax back into their natural plane. If a star caused the warp would be gone by now, erased, invisible, yet we see it today. Next, they tried the early solar system itself. Maybe when the planets were forming, the disk of gas and dust was already tilted in its outer regions. A built-in birth defect. This idea also collapsed under simulation. Even if the original disk had been warped during birth, The gravity of the giant planets would have ironed it flat by now. We started trying to come up with explanations other than a planet that could explain the tilt. But what we found is that you actually need a planet there, because if this was some feature of how the solar system formed, or if it was due to a star flying by, the warp would have gone away by now. This is the killer fact. Every alternative they tested produced a warp that should have decayed. But the warp is alive. It is fresh. It is being maintained. That means whatever is causing it is still there, still gravitating, still pulling. Think of it like a magnet held under a piece of paper covered in iron filings. Move the magnet, and the filings instantly fall into a pattern. Pull the magnet away, and the pattern collapses. The pattern only exists while the magnet is present. The Kuiper belt warp is the pattern. Something must be the magnet, and the magnet has to be inside the solar system right now. This is what separates Planet Y from all the wild theories that came before. The argument is not based on poetic speculation. It is based on the simple fact that gravity has a half-life. Disturbances decay, and a 15-degree tilt that has not decayed is screaming at astronomers that an active source is still in place. There is one more strange detail. The warp does not get smaller as you go farther out. It stays roughly the same beyond 80 astronomical units. This is consistent with a planet sitting in or near that region, dragging objects around it in a wide gravitational sphere of influence. Now, astronomers are scanning every patch of sky where the math says Planet Y could be hiding. The Vera Rubin Observatory in Chile, which began surveying in 2025, will turn its giant camera on regions previously ignored. It will photograph the entire southern sky every few nights, comparing images for anything that moves. If Planet Y is out there, it will move just enough between exposures to flag itself. But the warp is only the most recent clue. Long before astronomers found it, they had already noticed something else: a wall in space. A boundary where the Kuiper belt simply stopped existing. A cliff. The Kuiper belt has an edge that no one can explain. Sail outward from Neptune. You pass 30 astronomical units, then 40, then 45. The space around you is dense with icy bodies. The further you go, the more objects you should see, because the volume of space is increasing, and old solar system models predicted more material out here, not less. Then you reach 48 astronomical units, and the objects just stop. Earlier models of the Kuiper belt had suggested that the number of large objects would increase by a factor of 2 beyond 50 astronomical units, so this sudden drastic fall-off, known as the Kuiper cliff, was unexpected, and to date its cause is unknown. This is not a slow thinning, this is a wall. One side is crowded with icy worlds, the other side is nearly empty. Astronomers call it the Kuiper cliff, because that is exactly what it looks like in the data. A vertical drop in the number of objects right at the same location all the way around the Sunday. Picture an enormous frozen lake covered with rocks. Walk across it, and the rocks are everywhere. Then you cross an invisible line and suddenly the ice is bare. No rocks, no debris, nothing for hundreds of millions of miles. That is the Kuiper cliff. Why does this matter? Because every model of how the solar system formed predicts the opposite. The early sun was surrounded by a flat, dusty disk that extended outward for hundreds of astronomical units. That disk was where planets and comets and dwarf planets were born. There should be a smooth, gradual fade as you move away from the Sunday. Instead, we get a guillotine cut at 48 AU. Several theories have been proposed. None of them fully work. Some astronomers think the original disk simply ended there, but that raises the question of why. Others suggest that a passing star scraped away the outer material billions of years ago, leaving the belt with a hard edge. The problem with that idea is the warp we just discussed. A passing star should have left no permanent gravitational fingerprint. Then there is the planet theory. One explanation for the Kuiper cliff is that it arises as the consequence of resonant sculpting by a Mars-sized body just outside the cliff area. A Mars-sized body, right at the edge of the cliff. Read that again, because it lines up almost perfectly with the Planet Y hypothesis. Siraj's team independently arrived at a Mercury to Earth mass object. Older theories about the cliff suggested a Mars mass body. Different methods, different data, similar conclusion. Something planetary is sitting at or near the edge of the belt. A resonance is when objects move in step with a larger body. They feel its gravity at the same point in every orbit, and over millions of years, they either get locked in or thrown out. A planet sitting just past the cliff could have flung anything beyond a certain distance into deeper space, leaving the belt with a clean outer wall. The Kuiper cliff might be a crime scene. The missing objects are the victims. The planet is the killer, still walking the perimeter. But there is a darker possibility. What if the cliff is not a wall, but a doorway? What if the objects we should see beyond 48 AU are still there, but pulled into orbits we have not yet learned to find? Astronomers are now using the new Vera Rubin Observatory to do something previously impossible. Search past the cliff, look for the missing population, and see if they are hiding in tilted, elongated orbits that earlier telescopes never caught. Whatever is causing the cliff is doing something violent to the outer solar system. It is shaping space itself. It is rewriting where matter is allowed to live. And the cliff is only the start of the strangeness. Because farther out, past where the belt should not even exist, an object was discovered on an orbit so impossible it broke every model of how the solar system works. Its name is Sedna. In 2003, a small team at Caltech pointed a telescope at the far edge of the solar system and found something that should not have been there. A reddish, slow-moving dot, smaller than Pluto, roughly 600 miles across, drifting through the dark at a distance of 86 astronomical units, almost 3 times farther than Neptune. They named it Sedna, after the Inuit goddess of the cold sea. And once they calculated its orbit, the team went silent, because Sedna had no business existing. The problem is its perihelion. That is the closest point of its orbit to the Sunday. For most Kuiper belt objects, the closest approach is somewhere between 30 and 40 AU. Close enough that Neptune's gravity can still influence them. Close enough that an object can be tugged, scattered, or even ejected from the solar system. Sedna's closest approach to the Sun is 76 astronomical units. That number is shocking. It means Sedna never comes anywhere near Neptune. It cannot be a normal Kuiper belt object that wandered out. Nothing inside the known solar system has enough reach to put an object on an orbit like this. Sedna is detached, and it gets worse. Its farthest point from the Sun is roughly 900 astronomical units. That is more than 23 times the distance to Pluto. A single orbit takes Sedna more than 10,000 years to complete. Picture a long, lonely racetrack. Sedna is currently on the short side, close to the Sunday. For most of its life, it is hurtling outward into the deep cold of interstellar space, then crawling back. It will not return to this position until pyramids are dust and the constellations have rearranged themselves. So how did Sedna get there? The Sun's gravity alone is not enough to pull a body off the normal orbital paths and lift its perihelion that high. Something had to give Sedna a push, a gravitational kick, a force that lifted it out of the normal belt and stranded it on this enormous loop. Possible suspects are limited. A passing star, billions of years ago, could have flung Sedna outward as the young sun drifted through its birth cluster. This was a crowded environment, with thousands of newborn stars packed close together. Near misses would have been common, and the gravity of those stellar visitors could have warped local orbits permanently. Another suspect is a large hidden planet. If there is a massive object orbiting somewhere between Sedna's perihelion and aphelion, it could have slowly nudged Sedna into its current orbit through repeated gravitational interactions over the age of the solar system. This was one of the first clues that pointed to Planet 9. Mike Brown, the same astronomer who discovered Sedna, would later argue that the hidden planet hypothesis explained Sedna's orbit better than any other model. Batygin and Brown found that the presence of Planet 9 in its proposed orbit naturally produces Sedna-like objects by taking a standard Kuiper belt object and slowly pulling it away into an orbit less connected to Neptune. Sedna is a fossil. Its orbit has barely changed in 4 billion years because nothing close enough exists to disturb it. Whatever created that orbit did the work long ago, and then either left the solar system or settled into an orbit so distant we still cannot find it. The shape of Sedna's path is a memory, a frozen record of an ancient event, and the simplest explanation for that event is that something massive walked through this part of the solar system. Maybe a star, maybe a planet, maybe both. For years, Sedna was the only known object on this kind of orbit, a lonely outlier. Astronomers wondered if it might be a fluke, a statistical accident, something that happened once and never again. Then, 10 years after Sedna's discovery, the loneliness ended. Another object showed up, and it was on a strikingly similar path. The second object arrived in 2014. Two astronomers named Chad Trujillo and Scott Shepard announced they had been quietly tracking a faint dot at the edge of the solar system for 2 years. Its formal name was 2012 VP113. The casual name they gave it was Biden, because it had been spotted during the Biden vice presidency. Sedna was no longer alone. The new object had a perihelion of about 80 astronomical units, slightly farther from the Sun than Sedna's closest approach. Its orbit stretched outward for hundreds of AU before curving back. A complete trip around the Sun takes more than 4,000 years. 2 objects might not sound like much, but to astronomers, 2 is the start of a pattern. 1 is an anomaly. 2 is a clue, and the clue pointed in a strange direction. Both Sedna and the new object had orbits oriented in roughly the same direction in space. Their longest axes pointed toward a similar region of the sky. This was not what random gravitational scattering would produce. Random kicks should spread orbits in all directions, like dandelion seeds in the wind. Instead, these two had been aligned. Trujillo and Shepard ran the numbers. They argued that the alignment was not random. They suggested it might be caused by an unseen planet, somewhere out beyond Neptune, gravitationally shepherding the most distant objects into matching orbits. This was the first formal whisper of what would later become the Planet 9 hypothesis. Picture 2 arrows lying on a table, both pointing roughly the same direction. If you flicked them randomly onto the surface, they would land in different orientations. But if you placed a magnet under the table and the arrows were made of iron, they would line up. The alignment is evidence of an invisible force. Sedna and the new object are 2 of those arrows. Their alignment was the first sign that something was holding them in place. The discovery shook the astronomical community. For decades, the outer solar system had been considered finished, boring, a frozen archive with no surprises left. Now 2 objects on identical, impossible orbits suggested that everything beyond Neptune might be choreographed by a hidden hand. But 2 data points are still not enough. Skeptics pointed out that the sample size was tiny. Telescopes had been searching this region for years and had only found these 2. Maybe the alignment was just a coincidence. Maybe there were thousands of other distant objects with random orientations and we just had not seen them yet. The only way to know was to keep looking. Over the next decade, astronomers continued to scan the outer solar system. They found more extreme objects on long, elongated orbits. Most of them remained controversial. Some seemed to fit the alignment pattern, some did not. The data was messy. Telescopes can only see what is bright enough to catch. Shepard later said that finding objects in this region is like trying to spot fireflies on the dark side of the moon. Most of these worlds reflect almost no light. They are tiny, they are slow, and they spend most of their lives so far from the sun that they are essentially invisible. The fact that we have found any at all means there are probably hundreds more out there, possibly thousands, a whole hidden population of detached worlds, waiting in the dark. What pulled Sedna and 2012 VP 113 away from the rest of the solar system. Was it a single planet? Multiple planets? A passing star that came and went 4 billion years ago? Or something the math has not yet captured? The astronomers had a name for this rare class of objects now: sednoids. Detached, distant, aligned. For 10 years, only 3 sednoids were known: Sedna, 2012 VP 113, and a third object called Leleakuhonua, discovered in 2018. Then, in 2023, a Japanese team using the Subaru telescope in Hawaii found a fourth, and the fourth sednoid broke everything. A Japanese team had been quietly searching for distant objects for years. The project was called Fossil, short for Formation of the Outer Solar System, an icy legacy. They used the Subaru telescope on top of Mauna Kea, an 8-meter giant perched at 14,000 feet, where the air is thin enough to see almost to the dawn of the solar system. In 2023, the telescope picked up something faint, a speck of light moving against the stars at a glacial pace. The team flagged it. Then they waited. To confirm an orbit, you need to track an object over months, even years, watching how it shifts. By July of 2024, a team using the Canada-France-Hawaii telescope had confirmed the discovery. The object was real. It had an orbit, and the orbit was remarkable. They named it Ammonite, after the spiraled fossils of ancient sea creatures. Its formal designation was 2023 KQ-14. 2023 KQ-14 was discovered near its perihelion at a distance of 71 astronomical units. Its full orbit takes it from about 66 AU out to 252 AU. It loops the Sun on a journey thousands of years long, and like Sedna, it never comes anywhere close to Neptune. This made Ammonite only the fourth known sednoid, a precious addition to a tiny club of detached worlds. For the team in Japan, it was a career-defining discovery. But then they overlaid Ammonite's orbit on a map of the other 3 sednoids. Something was wrong. Sedna, 2012, VP 113, and Leleakuhonua all had orbits pointing roughly the same direction. Their long axes pointed toward a similar region of the sky. They were aligned. They were the foundation of the Planet 9 hypothesis. Ammonite pointed the opposite way, whereas the orbits of the 3 previously known sednoids appear to cluster between 0 degrees and 90 degrees. The orbit of 2023 KQ-14 points in the opposite direction at 271 degrees. This was not a small disagreement. Ammonite was not slightly off the pattern. It was the mirror image of the pattern. If the other 3 sednoids were pointing towards sunrise, Ammonite was pointing towards sunset. Picture 3 arrows on a table, all pointing east. A 4th arrow lands on the table pointing west. The alignment that seemed so clean a moment ago suddenly looks like noise. The team did simulations. They asked the question every astronomer in the world wanted answered. Could a single Planet 9, in its proposed orbit, produce all 4 sednoids? The simulation said no. The fact that Ammonite's current orbit does not align with those of the other 3 sednoids lowers the likelihood of the Planet 9 hypothesis, said Yukun Huang of the National Astronomical Observatory of Japan. Worse, the simulations showed that a Planet 9 in the originally predicted orbit would have ejected Ammonite from the solar system entirely. The fact that Ammonite is still here, on a stable orbit, means either Planet 9 does not exist, or it sits much farther out than the original models predicted. And Ammonite is no fluke. Its orbit is stable. Numerical simulations conducted by the Fossil team indicate that 2023 KQ-14 has maintained a stable orbit for at least 4.5 billion years. That stability is the killer detail. Ammonite has been on its anti-aligned orbit since the solar system was born. Whatever set up the orbits of the sednoids did it in the first 100 million years and then walked away. The architect of these orbits is not necessarily here anymore. For some scientists, this is the smoking gun. It is possible that a planet once existed in the solar system, but was later ejected, causing the unusual orbits we see today. A ghost planet, a world that came set everything in motion, and was then thrown out into interstellar space by Jupiter or Saturn during the chaotic early days. The Sednoids are its only remaining fingerprint. Or maybe Planet 9 is still out there, just farther, just colder, just more hidden than anyone expected. Either way, Ammonite changed the conversation overnight. The neat story of a single hidden shepherd planet was no longer enough. The solar system was hiding more than one secret, and the next question was even harder to answer. The Planet 9 theory was built on a foundation of 6 objects. Then Ammonite arrived and pulled out one of the support beams. To understand why this matters, you have to understand what the original argument looked like. In 2016, 2 Caltech astronomers named Konstantin Batygin and Mike Brown published a paper that stunned the world. They had been studying 6 of the most distant known Kuiper belt objects. The orbits of those 6 worlds were clustered together in space. Their long axes all pointed in a similar direction. Their tilts were similar. The alignment was striking. Batygin and Brown calculated the odds of this happening by chance. The number they got was about 0.007%. In other words, almost impossible. Their conclusion was that a hidden planet must be shepherding these objects. A massive world, somewhere in the outer solar system, slowly herding the smaller bodies into matching orbits over billions of years. They called it Planet 9. They estimated it at 5 to 10 times the mass of Earth, orbiting at about 600 astronomical units. This was a beautiful theory. It explained 6 oddities at once. It predicted that more aligned objects would be found as telescopes improved, and it gave astronomers a target to hunt. Then Ammonite refused to play along. Ammonite's orbit is detached, like Sedna's. It is stable, like Sedna's. It is ancient, like Sedna's. But it points in the opposite direction, and a Planet 9 in the originally proposed orbit cannot produce both Ammonite and the others. The simulations are clear. The numbers do not work. This is the problem with single suspect theories. They are elegant only as long as the evidence keeps pointing the same way. The moment one object breaks the pattern, the elegance collapses. There are 3 possible responses, and astronomers are currently debating all of them. The first response is that Planet 9 still exists, but is much farther away than originally proposed. If you push the hypothesized planet out to 1,000 or even 1,500 astronomical units, its gravitational influence weakens. It can still nudge orbits over long timescales, but it does so more gently, and it allows more diversity in the final result. This is the version most Planet 9 supporters now favor. The second response is that Planet 9 never existed. Maybe the original clustering of 6 objects was just bad luck, a statistical accident magnified by the fact that we cannot see most of the outer solar system. As telescopes find more objects, the apparent pattern dissolves. Other teams went after the conclusions, rather than the data, suggesting that those Kuiper belt objects really do have that pattern to their orbits, but that a wayward planet is not the only explanation. The third response is more dramatic. Maybe a planet was here long ago and was later ejected. A rogue, thrown out by Jupiter's gravity during the chaotic early years of the solar system. It set up the orbits we see today, and then disappeared into interstellar space. This third theory has a strange consequence. It means there might be a wandering planet drifting through the galaxy right now, a former member of our family that was kicked out before life began on Earth. Astronomers have already found rogue planets in deep space. We know they exist. The question is whether one of them used to be ours. Picture a family photo from decades ago. Someone in the back row was edited out. You can still see the gap where they used to stand. The way the others are positioned only makes sense if that missing figure was there at the time the photo was taken. Now they are gone, but the composition still carries the shape of their absence. The Sednoids might be that composition, a frozen group portrait of the early solar system. Ammonite's anti-aligned orbit might be the empty space where the missing figure once stood, and the consequences are enormous. If a planet was ejected, the solar system formed with at least 9 major bodies, and we only know 8 of them. Our textbook history of the planets is incomplete. But the planet that warped Ammonite is only one of several mysteries pulling at the Kuiper belt right now. Because long before Ammonite was found, the original 6 aligned objects were already raising a question no astronomer could ignore. What were the odds of finding their pattern by chance? The answer was so small that it sounded like science fiction. Before Planet 9 had a name, it had 6 fingerprints. In the years leading up to 2016, astronomers had catalogued a small handful of extreme trans-Neptunian objects. These were icy worlds with orbits so elongated that they crossed wildly different parts of the solar system. Their closest approaches to the Sun were beyond Neptune. Their farthest points reached deep into interstellar space. 6 of them stood out. Their names were forgettable. Long strings of letters and numbers like 2012 VP113 and 2002 GB32. But when Batygin and Brown plotted their orbits on a 3-dimensional map of the solar system, something jumped off the screen. The orbits were aligned. Not all 6 objects orbited at the same speed or distance. Their sizes varied, their tilts varied, but the direction their orbits pointed in space was strikingly similar. Imagine 6 racetracks of different lengths laid out next to each other. Each track is an oval. The long axes of all 6 ovals point roughly the same way. This is not what randomness produces. Random gravitational kicks should send orbits in all directions. If you simulate the outer solar system with no hidden planets, you get a fairly even distribution of orbit orientations, some pointing toward Vega, some pointing toward Sirius, some pointing toward the galactic center. You do not get 6 in a row pointing the same way. The simulation work of Batygin and Brown in 2016 showed that the orbits of various distant Kuiper belt objects exhibited strong clustering in both arguments of perihelion and physical space. The probability that this peculiar clustering happens by random processes is only 0.007%, which is almost impossible unless it is related to another unknown dynamical process. 0.007%. That is the kind of number that makes scientists pay attention. It is the statistical equivalent of finding 6 coins lined up heads up on a beach. Yes, it could happen by chance. But the simpler explanation is that someone placed them there. Batygin and Brown tried to find a placer. Their first guess was that there might be more distant Kuiper belt objects than we knew about, and the collective gravity of all those unseen worlds could be aligning the orbits of the 6 visible ones. They ran the simulations. To produce the observed alignment, this way would require the Kuiper belt to contain about 100 times more mass than it actually does. The hidden objects would have to outweigh Earth and Mars combined many times over. That much hidden mass would warp Neptune's orbit. We would have noticed. The theory died. Their second guess was a single, massive, distant planet. They ran simulations with different orbit configurations. Most of them did not produce the alignment, but one configuration kept working. A planet about 10 times the mass of Earth, orbiting on a track that was anti-aligned with the 6 objects. Anti-aligned meant the planet's closest approach to the Sun was on the opposite side of its orbit from the 6 bodies. In that configuration, the planet's gravity acted like a slow shepherd. Over hundreds of millions of years, it pulled the orbits of the smaller objects into a stable, anti-aligned cluster. The math fit. The alignment held. The theory of Planet 9 was born. The original 6 objects became the founding evidence. Every paper, every news article, every documentary about Planet 9 pointed back to them. 6 clustered orbits, one incredibly low probability of randomness, one elegant explanation, and here is the part that still fascinates astronomers a decade later. Even with Ammonite throwing a curveball, the original 6 remain stubbornly aligned. The pattern in those 6 orbits is real. It has not gone away. New objects discovered since 2016 have, on average, leaned slightly toward the predicted cluster, though not as cleanly as the original sample. Some critics argue that the six were a biased sample. Telescopes pointed in certain directions during certain seasons, picking up only the objects whose orbits happened to bring them close to the Sun during those windows. Brown and Batygin in 2019 developed a method to quantify the observational biases and concluded that the chance for the observed random clustering is only 0.2%. Even after accounting for bias, the alignment held. Less extreme than before, but still significant. The six are the spine of the Planet 9 argument. Remove them, and the theory falls apart. Keep them, and you are left explaining why six distant icy worlds, scattered across a region the size of 50 Saturns, march in formation through the dark. Either way, something out there is choreographing the dance. Something that has been doing it for billions of years. Something we still cannot see. And one of the strangest possibilities is not a planet at all. Numbers can be small. 0.007% is small. But in astronomy, small numbers carry enormous weight because they translate directly into how seriously the scientific community takes a discovery. Let me put that number in human terms. If you flipped a coin 8 times in a row and got all heads, you would think the coin might be loaded. The chance of that happening randomly is about 0.4%. Most people would suspect something was off. 0.007% is roughly the chance of flipping a coin 13 or 14 times and getting all heads. Try that yourself. You will not do it. Not today, not next week, not next year. The universe simply does not deal out those outcomes on the first try. This is the probability that the original 6 Kuiper belt objects ended up aligned by accident. It is so low that random chance is statistically excluded. Something is causing the pattern. The only question is what. But here is where it gets interesting. The 0.007 number assumes the sample was not biased. It assumes telescopes were equally good at finding objects pointing in every direction. They were not. So Batygin and Brown went back and accounted for the bias. They modeled where telescopes had actually looked when they had looked and how sensitive they were. The revised number was 0.2%, 2 in 1,000. Worse odds than rolling a perfect score in a single game of dice. That is still terrible odds. It means there is roughly a 99.8% chance that the alignment is real and a 0.2% chance it is a fluke. In other fields of science, 99.8 is a slam dunk. In particle physics, where the standard of proof is brutal, it would still be considered preliminary. The 5 sigma gold standard requires roughly 99.9995% certainty. Astronomers operate somewhere in between. They take 99.8 seriously, but they do not bet careers on it. This is why Planet 9 remains a hypothesis rather than a confirmed discovery. The evidence is strong. The evidence is not unbeatable. Until someone actually photographs a planet, the case stays open. But the statistical pressure has only grown. Over the years, more distant objects have been found. Some fit the alignment, some do not. The overall pattern, while messier than Batygin and Brown's original sample, has not gone away. Each new aligned object tightens the argument. Each anti-aligned object, like ammonite, complicates it. What is the cumulative likelihood that all this is random? Most working planetary scientists put it well below 1%. Mike Brown, the man who killed Pluto as a planet, has said publicly that he believes Planet 9, or something like it, is almost certainly out there. There is one more way to think about this. Imagine you walk into an empty room and find 6 pencils on the floor, all pointing roughly the same direction. You might shrug, maybe someone dropped them. Then you walk into the next room and find 6 more pencils pointing the same way. Then a third room, then a fourth. At some point, you stop looking for explanations and start looking for the person arranging the pencils. The Kuiper belt is full of rooms. Most of them are dark. We have only peeked into a few of them, and in every room so far, the pencils are leaning the same way. Now, here is what makes this even stranger. The Planet 9 hypothesis was originally proposed based on the alignment of 6 objects in 2016. The Planet Y hypothesis was proposed in 2025 based on the warp of more than 150 objects. These are 2 independent lines of evidence, using different methods, looking at different parts of the Kuiper belt, arriving at the conclusion that hidden planets must exist. The probability of 2 independent statistical anomalies, both pointing to hidden planets, both surviving aggressive skepticism, is much smaller than either alone. The case for at least one hidden world has gotten stronger over the past decade, not weaker. What we still cannot do is take a picture, tell the world, print a name in the textbooks. That picture might be only months away. But before we get to the hunt, there is one more strange wrinkle. Because Planet Y and Planet 9 are not the same object, they are 2 different ghosts, and both of them might be real. Astronomers used to talk about a single hidden planet. Now there are 2 on the table: Planet 9, Planet Y, different sizes, different distances, different gravitational effects. And no rule of physics says only one of them can exist. Let me lay them out side by side. Planet 9 was first proposed in 2016. It is hypothesized to be 5 to 10 times the mass of Earth, a super-Earth or a small Neptune. Its orbit is estimated to be between 400 and 800 astronomical units from the Sunday. It is the proposed shepherd of the 6 original aligned Kuiper belt objects. If real, it dominates a region of the solar system larger than the territory of any other known planet. Planet Y was first proposed in 2025. It is much smaller, between the mass of Mercury and the mass of Earth. Its orbit is estimated to be between 100 and 200 astronomical units from the Sunday. It is the proposed cause of the 15-degree warp in the orbits of Kuiper belt objects beyond 80 AU. Its tilt is at least 10 degrees out of the solar system's plane. Different scales, different jobs, different addresses. To differentiate their putative planet from Planet X, Siraj and his colleagues suggested a new name, Planet Y. Planet X refers to a distant high-mass planet, while Planet Y denotes a closer-in, lower-mass planet. This is important. The 2 hypotheses are not competing for the same evidence. They are explaining different anomalies. Planet 9 handles the clustering of the most distant detached objects. Planet Y handles the tilt of the moderately distant Kuiper belt. There is no contradiction in believing both exist, and there is no contradiction in believing both might be wrong. Astronomy is full of elegant hypotheses that died when better data arrived. Planet Vulcan, the hypothesized world between Mercury and the Sun, lasted for decades in the 19th century before Einstein's general relativity explained away the orbital anomaly that suggested its existence. Vulcan never existed. The data was real, but the explanation was different. This is the situation right now with the outer solar system. We have multiple anomalies. We have multiple proposed planets. We have no direct images. Until a telescope catches one of these worlds in motion, every hypothesis stays on the board. But here is what makes the current moment unusual. The skeptics have been narrowing the alternative explanations. Passing stars, self-gravity of the belt, cumulative perturbations from the giant planets. One by one, these have been tested and found wanting. Either they cannot produce the observed effects, or they would have decayed long ago. The space of plausible non-planet explanations is shrinking. The space of plausible planet explanations is expanding. Picture a courtroom. The prosecution does not have a video of the crime, but they have fingerprints on the doorknob, footprints in the carpet, a fiber from a jacket on the chair. Each piece of evidence alone could have a non-criminal explanation. Together, they paint a picture, and the picture has a shape that looks more and more like an actual perpetrator the longer you stare. The Kuiper belt anomalies are evidence of that kind. The warp, the cluster, the cliff, the sednoids. Each one has alternative explanations. Each one survives scrutiny when those alternatives are tested. Each one keeps pointing back at the same conclusion. There are planet-sized objects hiding in our own solar system, possibly 2 of them, possibly more. Some researchers have proposed that there could be additional unseen worlds even farther out, sculpting populations of objects we have not yet discovered. A 3rd or 4th hidden planet would not be ruled out by current data. It would just be invisible to current telescopes. The deeper we look, the more rooms in the dark house we find. And every room we open has hints of someone who was there before us. 2 hidden worlds, possibly more, all within the gravitational reach of our own Sunday, all capable of being mapped, named, and photographed in our lifetimes. The race to find them is already underway, and the most aggressive search strategy is not even using visible light, it is hunting for heat. If a planet is too dark to see in visible light, you change what you are looking for. You stop hunting for reflected sunlight, you start hunting for warmth. Every object in the universe with a temperature above absolute zero emits infrared light, heat radiation. Even the coldest worlds glow faintly in the infrared because they have leftover heat from their formation, or because they are warmed slightly by the distant Sunday. A planet beyond Neptune would be extremely cold, maybe minus 370 degrees Fahrenheit, but it would still emit a tiny, faint infrared signal, and that signal can be detected by space telescopes designed to see in those wavelengths. This is the strategy that researchers have started using to hunt for Planet 9. In 2025, a team led by Amos Chen at National Tsinghua University in Taiwan published a striking result. Analysis of far infrared data from the AKRI Space Telescope has identified 2 candidate objects emitting the expected thermal signature and located where a hypothesized Planet 9, with a mass 5 to 10 times that of Earth and an orbit 400 to 800 astronomical units from the Sun, should be. 2 candidates, both glowing faintly in the infrared, both in the region of sky where Planet 9 should be hiding. This is huge, or it might be nothing. We do not know yet. The Akari telescope was a Japanese space mission that surveyed the sky in infrared light between 2006 and 2007. Its data is now nearly 2 decades old. The team combined those observations with an even older survey, the IRIS satellite from 1983. 23 years separated the 2 surveys. This is the key. The epochs of these 2 surveys were separated by 23 years, which is large enough to detect Planet 9's approximate 3 arc-minutes per year orbital motion. In 23 years, a planet at 400 AU would move just slightly across the sky. Not much, but measurably. The team looked for objects that appeared in one survey but had shifted position by the time of the other survey. Background galaxies would not move. Stars would barely move. A planet in our solar system would move enough to be detected. They found 2 such candidates, both in the right region, both with the right brightness for a Planet 9-sized object, both with the right amount of motion. So why are we not celebrating the discovery? Because 2 candidates is not enough. First of all, this is only 2 data points, and astronomers never accept something so flimsy. There's too much chance it's just noise. The Akari and IRAS data could contain ghosts, cosmic rays that hit the detector at the right moment, background galaxies that flickered briefly, asteroid belt objects masquerading as something farther out. Any of these could create the appearance of a planet without there actually being one. Mike Brown, the original Planet 9 proposer, has said that even if the candidates are real, they are probably too far out to be the version of Planet 9 he originally predicted. Either his prediction needs to move, or the candidates are something else entirely. To confirm one of these candidates as a real planet, follow-up observations would need to find the same object in the same location with the right motion in modern telescope data. That work is currently happening. Several teams around the world are scrutinizing the candidates. Results could come within a year or 2. If even one of the candidates turns out to be a real planet, it would be the discovery of the century. The first new planet found in our solar system since Neptune in 1846. a target large enough to send a probe to, a world we could one day photograph in detail. If both candidates dissolve under closer inspection, the hunt continues. There are more infrared archives to search, more techniques to try, more sky to scan. The infrared approach has one enormous advantage over visible light. It does not depend on the Sunday. A planet at 400 AU reflects almost no sunlight back to us, but it cannot hide its own heat. Even the coldest worlds glow. There is a poetic irony here. The planet that has eluded telescopes for a century, the planet that has stayed hidden behind its own darkness, may be revealed by something it cannot suppress, its own faint warmth in the cosmic cold. The hunters know exactly where to look, and the next generation of telescopes is about to make the hunting easier than ever. To understand why finding Planet 9 is so hard, you have to picture what it actually looks like. Imagine you are floating 400 astronomical units from the Sunday. That is 60 billion miles. Sunlight at this distance is about 160,000 times weaker than what reaches Earth. The Sun is still the brightest star in your sky, but it is no longer a disk. It is a dazzling point of light, smaller than Venus appears from your backyard. Now, imagine you are this hypothetical planet. You are roughly the size of a small Neptune. Your surface is frozen solid, methane ice, nitrogen ice, maybe water ice underneath. The temperature is so cold that the chemistry of life as we know it would freeze in milliseconds. You reflect almost no light back toward Earth. Why? Because there is barely any light hitting you to begin with. And what does hit you, you absorb. Even bright surfaces can only bounce back what they receive, and there is almost nothing to bounce. From Earth, you appear as a single faint point of light, possibly as dim as magnitude 22 or 23. That is roughly 50,000 times fainter than the dimmest star the human eye can see. Only the largest telescopes on Earth, plus space-based observatories, can detect light at this level. And here is the cruelest part. You move slowly. A planet at 400 AU takes more than 8,000 Earth years to complete one orbit. From night to night, your position barely changes. You would appear nearly stationary against the background stars, hiding among 10,000 other faint points of light, indistinguishable from a distant galaxy or a slow asteroid. This is why traditional planet searches have failed for decades. Telescopes scan the sky, catalogue the faint points, and try to detect motion. The slower the motion, the longer the survey has to run. To catch Planet 9 moving against the background, you need observations separated by years, not nights. Infrared changes the math. In the infrared, the contrast game flips. A planet at 400 AU still reflects almost no sunlight, but it has its own heat. Even at minus 370 degrees Fahrenheit, it glows faintly. And in the infrared, the background sky is much darker than invisible light. The stars and galaxies are still there, but their relative brightness is shifted. A cold planet stands out against the cold background sky more easily than a dim planet stands out against the bright background stars. This is the technical advantage that the Akari search exploited. By looking in far infrared wavelengths, the team filtered out the noise of starlight and focused on objects with the specific temperature signature that a Planet 9-sized world would have. The challenge is that the AKA data is 2 decades old and the resolution is low. Modern infrared space telescopes, like the James Webb Space Telescope, have far better sensitivity. The problem is that Webb has many other priorities, and dedicating its time to searching a large area of sky for a hypothetical planet is a tough sell to the scheduling committee. What might solve the problem is a new generation of wide-field surveys. The Vera Rubin Observatory in Chile is the most important of these. It will photograph the entire southern sky in visible light every few nights for a decade. Its camera is the largest digital camera ever built. Every object brighter than magnitude 24 will be catalogued and tracked. If Planet 9 is brighter than that limit, Rubin will find it within the first few years of operation. Picture a vast warehouse, dark, and silent. You are looking for one object inside it. You cannot see it directly, but you have just been handed a thermal camera, and you know roughly where to point. That is where astronomy is right now. The thermal cameras are warming up. The maps are being drawn. The search has narrowed from the entire warehouse to one specific corner, and the next decade is going to deliver answers that have been waiting for 2 centuries. On a mountain in Chile, 8,800 feet above sea level, sits the most powerful sky survey telescope ever built. Its full name is the Vera C. Rubin Observatory. It is named for the American astronomer who first found evidence for dark matter in galaxies. The mountain is Cerro Pachon, in the dry Atacama region of northern Chile, where the air is so still and clear that distant stars do not even twinkle. In June of 2025, the observatory achieved first light. Its giant mirror, more than 27 feet across, captured its first images of the sky. By the end of 2025, the telescope began its signature project, the Legacy Survey of Space and Time, the LSST, a 10-year sweep of the entire southern sky, photographed every few nights. This is the telescope astronomers have been waiting for. The camera attached to it weighs 3 tons and contains over 3 billion pixels. It is the largest digital camera ever built. Every exposure captures an area of sky larger than 40 full moons. In a single night, the LSST will image thousands of square degrees. Over 10 years, it will produce the most complete time-lapse map of the night sky in human history. For the hunt for hidden planets, this is everything. Current estimates suggest that the LSST will find between 20,000 and 40,000 new Kuiper belt objects in its first few years. The total number of known objects beyond Neptune will increase by a factor of 5 to 10, almost overnight. We're going to be increasing the number of known objects by something like a factor of 5 to 10. Stop and absorb that. Right now, astronomers have studied a few thousand distant icy worlds. The LSST will give them tens of thousands more. The statistical clarity of every theory about the Kuiper belt will sharpen by orders of magnitude. If the orbital warp causing the Planet Y hypothesis is real, the LSST will make it undeniable. With 10 times more data points, the warp will either jump out as a screaming signal or fade into noise. Either result advances science. If the alignment causing the Planet 9 hypothesis is real, the LSST will either confirm it with overwhelming statistics or kill it. The original 6 aligned objects will be joined by hundreds more sednoids and extreme TNOs. If most of them align, the case for a shepherd planet becomes nearly airtight. If most of them do not, the theory is in serious trouble. And there is a real possibility that the LSST will photograph one of these planets directly. Planet Y, if it exists, sits at about 150 AU. At that distance, with a body roughly the size of Mercury, it would shine at about magnitude 21 or 22 in visible light. That is bright enough for the LSST to detect easily. Planet 9, if it exists, would be harder. At 400 to 800 AU, it would be much fainter, but even there, the LSST could catch it if the planet is closer to the brighter end of the predicted range, or if it is larger than the smaller predictions allow. If Planet Y exists, within the survey's first few years, we may either see it or gather stronger proof of its gravitational effects. Within the survey's first few years, that means within this decade, possibly within 2027 or 2028, possibly while you are still reading the news about it. The team behind the LSST has already prepared the algorithms. Software is being developed right now that will scan every new image, compare it to the previous image of the same patch of sky, and flag anything that moves. Slow movers like Kuiper belt objects and hypothetical hidden planets will appear in the data as faint smudges drifting against the stationary stars and galaxies. A planet at 150 AU would shift its position by a measurable amount every few weeks. A planet at 400 AU would shift more slowly, but still detectably over months. The LSST is designed for exactly this kind of patient, careful tracking, astronomers describe the coming decade as a golden age for outer solar system research. Mike Brown himself, the man who killed Pluto and predicted Planet 9, has said that he expects either confirmation or rejection of his hypothesis within 10 years. The wait is almost over, but the LSST is not the only source of new evidence. Because while the cameras are scanning visible light, other telescopes have already started finding things no one expected: hidden structures inside the Kuiper belt itself, inner clusters, inner kernels, patterns that should not exist. The Kuiper belt is not uniform. It has substructure, layers within layers, clusters within clusters. And one of the most surprising discoveries of the last few years is that this substructure goes deeper than anyone realized. Back in 2011, researchers identified a curious feature near 44 astronomical units. Researchers found a cluster of 189 objects on a similar orbit within the Kuiper belt, that region of icy rocks out past Neptune in the solar system, located 44 astronomical units away from the Sun. That cluster is called the kernel of the Kuiper belt. A kernel, a tight grouping of objects orbiting the Sun in roughly the same way, packed into a small region of space within the larger belt. This was strange enough on its own. It hinted that something had organized this part of the belt long ago. Maybe a planet that drifted through and shepherded objects into a stable resonance. Maybe a feature of how the solar system originally formed. In 2025, the picture sharpened. Researchers at Princeton announced something new. Researchers at Princeton have now found another, more compact cluster of objects they're calling the inner kernel. This inner kernel was discovered through refining orbital data from 1,650 Kuiper belt objects that were plugged into a clustering algorithm. The new cluster is located roughly 43 astronomical units from the Sun, 43 astronomical units. Just inside the original kernel, a second, more compact cluster sitting right next to the first one. Hidden inside the belt's hidden structure, this is not what a simple solar system would produce. A simple solar system has a flat, smooth disk that thins out gradually. Our solar system instead has bumps, clumps, layers of organized material at specific distances, separated by gaps where almost no objects exist. Each of these features is a clue. Together, they sketch the history of forces that have shaped the belt over billions of years. The inner kernel was found using a clustering algorithm. The team ran orbital data from 1,650 Kuiper belt objects through software designed to find subtle groupings. The result was the discovery of a population of objects that share similar orbital parameters, similar distances, similar tilts. A family. Families are evidence of common origin. They suggest that all the members were either born in the same place at the same time, or that they were captured into the same orbital resonance by a larger gravitational influence. Picture a calm lake again. Throw a stone in, and ripples spread outward. Throw a handful of stones, and the ripples interfere with each other, creating patterns. The Kuiper belt is the lake. The stones are the planets, the passing stars, the migrating giants of the early solar system. The kernel and the inner kernel are patterns in the water, where ripples from old events still resonate. Neptune is part of this story. As the planet migrated outward during the early solar system, it scattered Kuiper belt objects into specific orbital resonances. The 2-to-1 resonance, the 3-to-2 resonance. Pluto sits in the 3-to-2 resonance with Neptune, locked in a gravitational dance that keeps it stable for billions of years. But the inner kernel and the original kernel sit in regions that should not be strongly influenced by Neptune alone. Something else may have helped shape them. A migrating ice giant that no longer exists, a passing star, maybe even a hidden planet at a different distance. The discovery of the inner kernel also matters for the search for Planet Y. If Planet Y is at 100 to 200 AU, its gravitational influence should reach inward and affect objects in regions like the kernel. The fact that we are now finding new structures in this part of the belt means the LSST will have much sharper data to test the Planet Y hypothesis with. The Kuiper belt is not a graveyard. it is a record. Every cluster, every cliff, every detached sednoid is a line in a story that has been writing itself for 4.5 billion years. We are only just starting to read it, and some of the lines are not even on the page we expected, because farther out, in regions where the belt should be empty, telescopes have found objects on orbits that defy everything we thought we knew about how planets shape their neighborhoods. Objects that are not just tilted, but turned completely sideways. Most objects in the solar system orbit the Sun in roughly the same flat plane. The plane of the 8 planets is the reference. Earth, Jupiter, Saturn, Neptune all move in a thin disk, like beads sliding around the same flat tray. But some objects in the outer solar system do not. A small set of distant, icy worlds has been found on orbits that are nearly perpendicular to the planetary plane, tilted 90 degrees, up and over, going around the Sun on a path that takes them above the North Pole of the solar system, then below the South Pole, and back again. This is bizarre. A perpendicular orbit is hard to create. Gravity prefers flat. The original disk of gas and dust that formed our solar system was flat. The planets that condensed out of it kept that flatness. To tilt an object by 90 degrees, you need a serious gravitational disturbance, something powerful, something persistent. The discovery of perpendicular Kuiper belt objects was one of the more eerie predictions of the Planet 9 hypothesis. A predicted consequence of Planet 9 is that a second set of confined objects should also exist. These objects are forced into positions at right angles to Planet 9 and into orbits that are perpendicular to the plane of the solar system. 5 known objects fit this prediction precisely. 5 objects, 5 icy worlds, all on orbits that should not exist, all pointing the same way Planet 9 predicted they would. This was one of the most surprising moments in the Planet 9 story. Batygin and Brown had built their hypothesis based on the aligned cluster of 6 normal sednoids. The math of their model also predicted that a second population should exist, not aligned with the rest of the planets, not aligned with the sednoids, but tilted at right angles to everything. When they checked the catalogues of known objects, they found them. Suddenly, I realized there are objects like that, recalls Brown. In the last 3 years, observers have identified 4 objects tracing orbits roughly along one perpendicular line from Neptune and 1 object along another. This is the kind of evidence that excites astronomers. It is one thing to fit a hypothesis to existing data. It is another thing entirely to make a prediction about objects that have not been associated with your theory. Look in the catalogue and find them already sitting there. The perpendicular objects are unsung heroes of the Planet 9 story. They do not get the headlines that Sedna or Ammonite get, but their existence is one of the strongest indirect arguments for a hidden planet. Without something massive tilting them, they should not be where they are. How does a planet create perpendicular orbits? Through a long, slow gravitational dance called a Kozai resonance. Over millions of years, the gravity of a distant inclined planet can pull the orbit of a smaller body up and over, swapping its eccentricity for inclination and back again. The end result is an object on a wild, tilted orbit that loops around the Sun in a way no normal solar system process can produce. If Planet 9 is real and tilted, the Kozai resonance is what would have created these perpendicular orbits. The math works. The objects exist. The puzzle pieces fit. Some of these tilted worlds have orbits so extreme that they cross the orbits of multiple planets at steep angles. They are like wrong-way drivers on a flat highway, plunging through the planetary plane and continuing into the dark above or below. What would it be like to stand on one of these worlds? Imagine looking up. Instead of the familiar band of the Milky Way stretching across the sky, you would see the entire solar system tilted to one side. The Sun would rise and set on a strange diagonal track. Other planets would appear far below or far above their usual positions. Your sky would feel wrong, like the universe had been rotated. These objects are real. They are documented. They are sitting in our solar system right now, tilted into impossible angles by a force that no other model adequately explains. And here is the chilling part. The perpendicular objects do not just fit Planet 9, they independently support it. They are an entirely separate line of evidence from the original aligned 6. The fact that two independent populations of objects, in two completely different orbital regimes, both point toward the same hidden planet is what keeps the hypothesis alive, even after Ammonite threw cold water on the sednoid alignment. The Kuiper belt is becoming a courtroom where the witnesses keep showing up to give the same testimony, and the testimony all describes the same suspect. We are halfway through the case now, halfway through the story of what is pulling on the most distant edges of our solar system. The evidence so far points to multiple hidden hands, multiple ghost planets, maybe more than that, because the next clue is going to take us out of the planet hypothesis entirely. What if the thing pulling on the Kuiper belt is not a planet at all? What if it is something far stranger? Before reaching for hidden planets, scientists had to rule out the obvious suspect, Neptune. Neptune is the gravitational bully of the outer solar system. It is 17 times the mass of Earth, and it sits at the inner edge of the Kuiper belt at about 30 astronomical units. Its gravity reaches deep into the icy ring beyond it, scattering smaller objects, locking some into resonances, and flinging others into wildly different orbits. For decades, astronomers assumed Neptune was responsible for almost every strange feature of the Kuiper belt: the tilts, the clusters, the detached objects. Surely a planet as massive as Neptune, sitting right at the doorstep, could explain everything. It cannot. Neptune's gravitational reach has a hard limit. Beyond a certain distance, its influence drops off sharply. The math is straightforward. Gravity weakens with the square of distance. By the time you reach 50 astronomical units, Neptune's pull on a small object is only 1/3 of what it is at 30 AU. By 100 AU, it is 1/9. By 200 AU, it is barely a whisper. Sedna's closest approach to the Sun is 76 AU. Ammonite's is 66 AU. Both objects stay so far from Neptune that the giant ice planet can do almost nothing to them. This is the central problem with the Neptune-only theory. The objects that need explaining are exactly the ones Neptune cannot reach. Of the several thousand known Kuiper belt objects, the team honed in on that subset because those objects aren't gravitationally influenced by Neptune. Neptune has a really strong grasp on the outer solar system, said Siraj. Siraj's team deliberately filtered out anything that could be touched by Neptune. They wanted a clean sample. They wanted to see what was happening in the regions where the known planets could not be the cause. And it was in that filtered sample, in that quiet zone beyond Neptune's grasp, that the 15-degree warp appeared. This is one of the cleanest scientific arguments in the entire hidden planet debate. If Neptune cannot reach these objects, but their orbits are warped, then something else must be reaching them. And that something has to be inside the solar system, because external forces like passing stars would have left signatures that decayed long ago. Neptune also fails to explain the Kuiper cliff. The 2-to-1 resonance with Neptune sits at about 48 astronomical units, exactly where the cliff begins. So Neptune does play a role in shaping the cliff edge, but it cannot account for the brutal emptiness beyond. If the original disk extended outward to 100 or 200 AU, Neptune's gravity would not have stripped that material away. Something else had to do it, and Neptune cannot explain the sednoids at all. Their perihelions are so far from Neptune that the planet would have needed 100-fold boost in mass to influence them. There is no such boost. Neptune is exactly as massive as it has always been. There is one more failure mode for the Neptune theory: the perpendicular objects. The 5 known worlds tilted 90 degrees from the planetary plane. Neptune cannot tilt anything to 90 degrees. Its gravity acts within the planetary plane and tends to keep objects flat. Producing a perpendicular orbit requires a tilted, distant gravitational source. Neptune is neither tilted nor distant. This is why astronomers have moved beyond the easy answer. Neptune is a giant. Neptune is powerful. But Neptune is also limited. And the puzzle in the outer solar system is happening exactly in the regions where Neptune's power ends. So the search has expanded. If the known planets cannot explain the data, the next candidates have to be unknown planets, or unknown forces, or unknown objects entirely. This is where the science gets weird, because some of the proposed explanations for what is pulling on the Kuiper belt are not even planets in the traditional sense. They are stranger, darker, and harder to find. One of them is a planet that does not live here anymore. A world ejected from the solar system billions of years ago, leaving its fingerprint on the orbits we still see today. What if the planet pulling on the Kuiper belt was never born in our solar system? Astronomers have long known that the galaxy is full of rogue planets, worlds without a star, cold, dark, drifting through interstellar space. Estimates suggest there may be more rogue planets in the Milky Way than there are stars. Trillions of orphaned worlds, ejected from their home systems by gravitational encounters with siblings. Most of them simply drift. But occasionally, by chance, one of them passes close enough to a star to be captured. Gravitational physics allows this. A rogue planet entering a stellar system at exactly the right angle and speed can become a permanent member of that system, orbiting on a wide, eccentric loop. This is one of the live hypotheses for Planet 9. The idea is straightforward. Long ago, when the Sun was still young and embedded in its birth cluster, a rogue planet wandered close to our solar system. The Sun's gravity, combined with the influence of nearby sibling stars, captured the wanderer. It settled into an orbit far beyond Neptune. It has been there ever since. This would explain a lot. A captured planet would not have formed in the standard way that the other planets did. It would not necessarily orbit in the same plane. Its orbit could be eccentric, tilted, or even retrograde. It could be made of materials that do not match the chemistry of the inner solar system, and it could have entered on an orbit that places it exactly where Planet 9 should be. In their initial article, Batygin and Brown proposed that Planet 9 formed closer to the Sun and was ejected into a distant eccentric orbit following a close encounter with Jupiter or Saturn during the nebular epoch. Then, either the gravity of a nearby star or drag from the gaseous remnants of the solar nebula reduced the eccentricity of its orbit. The capture scenario is one of three possibilities Batygin and Brown have explored. The other two are in situ formation, meaning the planet formed where it is, and the ejection and stabilization scenario, where it formed near the giant planets and was kicked outward. All three are physically possible. None has been ruled out, but the rogue capture idea has one feature that the others do not. It places the origin of Planet 9 outside the solar system, which means the planet, if real, may have formed around a different star entirely. Its rocks, its ice, its potential atmosphere, all of it would carry the signature of another star system, a different stellar nursery, a different chemistry. Stop and let that settle for a moment. There is a real chance that one of the planets in our solar system was born somewhere else, around another sun, in another part of the galaxy, and then drifted here billions of years ago and got caught. If we ever find Planet 9 and study its surface, the chemical fingerprints will tell us different ratios of oxygen and hydrogen isotopes, different proportions of rare elements. The differences would be subtle but measurable, and they would prove that our solar system has a member that does not belong to it by birth. There is more. Even the smaller planet Y could potentially be a captured object. Siraj's team has noted that the inclined orbit needed to produce the 15-degree warp is more naturally explained by a captured planet than by one that formed within the original protoplanetary disk. Disks tend to produce planets that share the same plane. Tilted planets are easier to make through capture. This raises a deeper question. How many of the planets we know are actually originals? Earth, the rocky inner worlds, the gas giants. We have always assumed they all form together from the same disk. What if that is wrong? What if our solar system has been collecting captured wanderers throughout its history, and we have only just begun to notice? The capture theory also fits with what we are learning about other star systems. Astronomers have detected planets in extremely wide orbits around distant stars, orbits that are hard to explain through standard formation models. Capture is becoming a more accepted mechanism every year. Picture a busy train station. Most passengers got on at the same place. They started together and have been riding together. But occasionally, someone steps onto the train at a later stop. They look like a normal passenger. They sit in a normal seat, but their ticket says they came from somewhere else entirely. Planet 9, if it exists, might be that passenger. And the strangest possibility of all is that the wanderer might not even be a planet. It might be something far denser, far stranger, and far harder to see. Take a moment with this one, because the next hypothesis sounds like science fiction, but it is being seriously discussed in peer-reviewed journals. What if Planet 9 is not a planet at all? What if it is a black hole, specifically a primordial black hole? These are hypothetical objects believed to have formed in the first fractions of a second after the Big Bang, when the universe was still hot and dense enough for tiny regions of space to collapse under their own gravity. Unlike the black holes formed from dying stars, primordial black holes can be very small. Some theories predict that they could exist with the mass of a planet, but compressed into a region the size of a grapefruit-sized object with the mass of 5 to 10 Earths. If one of these objects is sitting in the outer solar system, it would have all the gravitational properties astronomers attribute to Planet 9. It would shepherd distant Kuiper belt objects into aligned orbits. It would produce the perpendicular orbits. It would warp the orbital plane of the sednoids, but it would not glow. It would not reflect sunlight. It would emit only a faint, almost undetectable trickle of Hawking radiation. It would be the perfect hiding object, hovering in our solar system in plain sight, completely invisible to every telescope ever built. Others think that this supposed Planet 9 is actually a primordial black hole, one that is too small to be seen with modern technological methods. This is not a fringe idea. Two physicists, Jakob Schultz and James Unwin, published a paper in 2019 proposing that the orbital anomalies attributed to Planet 9 could be explained by a primordial black hole captured by the early Sunday. Their math worked. Their predicted mass and orbital parameters matched the existing Planet 9 hypothesis almost exactly. The implications are staggering. Primordial black holes have been proposed as a possible explanation for dark matter, the mysterious substance that makes up most of the mass in the universe. If one is sitting in our solar system, it would be the first direct evidence that primordial black holes exist at all. Finding it would solve one of the biggest mysteries in cosmology. It would also be terrifying. A primordial black hole in the outer solar system is not a threat to Earth. Its orbit is far away, and its gravitational reach is the same as any planet of the same mass. But the idea of an invisible, indestructible object lurking in our backyard, with the power to swallow anything that falls into it, is the kind of fact that changes how you see the night sky. How would we ever detect it? There are two main approaches. The first is to look for tiny flashes of light. When small comets or asteroids pass close to a primordial black hole, they would be torn apart by tidal forces and consumed. The accretion of material would produce a brief flash of high-energy radiation. Searches for these flashes are underway, but none has been confirmed. The second approach is more direct. Send a spacecraft to look. The sun's own gravity could be used to slingshot a small, fast probe into the outer solar system, where it would search for evidence of an unseen mass. The challenge is enormous. Even at top speeds, such a mission would take decades to reach the target distance, and the probe would have to know exactly where to look, because the search area is vast. Most astronomers still favor the planet hypothesis over the black hole one. Planets are more common. They are easier to form. They have direct precedence in other star systems. Primordial black holes, in contrast, have never been confirmed to exist. But the black hole hypothesis stays on the table because of one inescapable fact. If Planet 9 is a normal planet, we should have found it by now, or at least found tighter constraints on where it is hiding. The continued failure to spot it makes some scientists wonder whether the suspect is not just dim, but invisible by nature. Picture a magician who keeps making things disappear. Eventually, you stop asking how good the trick is and start asking what is really being done. Whether or not the black hole hypothesis is correct, it serves as a reminder. The thing pulling on the Kuiper belt might not be a familiar object. It might be something we have not yet learned to see. And there is at least one more radical possibility. What if there is no hidden object at all? What if the warp and the alignment are real, but the cause is not a planet, not a star, not a black hole, but something even more fundamental? What if our theory of gravity itself is incomplete? Imagine, for a moment, that physics has been hiding a flaw for over a century. For all of modern astronomy, our understanding of gravity has been built on Isaac Newton and Albert Einstein. Newton gave us the law of universal gravitation. Einstein refined it with general relativity. Together, they predict the motions of planets, stars, and galaxies with extraordinary precision. Or so we thought. In the 1970s and 80s, observations of distant galaxies revealed a problem. The stars in those galaxies were rotating too fast for the gravity of the visible matter to hold them together. Either there was an enormous amount of invisible matter, called dark matter, providing the extra gravity, or the laws of gravity themselves were different at galactic scales than at planetary scales. The dark matter explanation won the mainstream consensus. But a minority view persisted, a theory called modified Newtonian dynamics, or MOND, suggested that gravity behaves differently when accelerations become very small. In regions where objects are barely being pulled at all, like the outskirts of galaxies, gravity gets a small boost. No dark matter required. For decades, MOND remained on the fringe of physics. It was hard to test. The relevant accelerations are nearly impossible to measure in laboratories. And the solar system, where every planet is firmly within Newton's regime, seemed irrelevant to the debate. Then someone realized that the outer Kuiper belt is the perfect testing ground. We wanted to see if the data that support the Planet 9 hypothesis would effectively rule out MOND, Brown said. And ultimately, they found that the strange clustering could indeed be because of MOND. Mike Brown, the same astronomer who proposed Planet 9, ran the experiment. Together with his colleague Mather, he tested whether the observed clustering of distant Kuiper belt objects could be explained by MOND instead of by a hidden planet. The result was unexpected. Mather and Brown proposed that over the course of millions of years, the orbits of some outer solar system dwellers could have been gravitationally dragged. Instead of being aligned with the rest of the solar system, they find alignment with the gravitational field of the Milky Way. Mather said the duo found that the alignment was striking. If MOND is correct, the orbits of the most distant Kuiper belt objects should slowly drift into alignment with the gravitational field of the Milky Way galaxy itself, not with a hidden planet, with the diffuse gravitational pull of our home galaxy. When Brown and Mather checked, the alignment was real. The orbits did appear to line up with the galactic gravitational field. This is not proof that MOND is correct. The data is limited. The effect could be a coincidence, or it could be partially driven by selection bias in the catalogue of known objects. But it is the first direct test of MOND in a solar system context, and the result is consistent with the theory. If MOND turns out to be the real explanation, the implications are enormous. Planet 9 would not exist. Planet Y might not exist. The decades-long search for hidden worlds would have been chasing a ghost. But in exchange, we would have discovered that gravity itself works differently than Newton and Einstein taught. This is the kind of revolution that comes along once a century, and it would be one of the strangest places it could be discovered, in the quiet edges of our own backyard. Most physicists are skeptical. General relativity has passed every test ever thrown at it, including the detection of gravitational waves and the imaging of black hole shadows. To overturn it now would require evidence far stronger than orbital alignments of icy bodies. But Mond has not been disproven either. It remains a minority, but credible position. The beauty of the situation is that the upcoming flood of new data from the Vera Rubin Observatory will help settle the question. If Mond is correct, the new objects discovered should also align with the galactic field. If a hidden planet is correct, the new objects should align with the planet's expected position. The signatures are different. The data will eventually decide. For now, the answer is that we genuinely do not know. The Kuiper belt could be telling us about a hidden world or about a hidden flaw in our deepest theories of physics. Either answer changes the textbooks, but there is one more theory we have not yet explored, a theory that says the planet was here, did its work, and then left forever. What if the planet that bent the Kuiper belt is no longer here? This is the boldest of all the recent hypotheses. It says that yes, a planet did warp the sednoids and shape the outer solar system, but that planet was thrown out long ago. What we see today is just the gravitational scar tissue from an event that ended billions of years before life on Earth even began. Some scientists think that maybe there was a giant planet in the solar system, but over time it was pushed away and flew off into space. And that's why we now see such strange and different orbits in these distant objects. The early solar system was a violent place. The 4 giant planets, Jupiter, Saturn, Uranus, and Neptune, did not always sit where they do today. Computer simulations suggest that they migrated significantly during the first few 100 million years. Jupiter may have wandered closer to the Sun and then swung back outward. Saturn may have engaged in a gravitational dance with Jupiter that reshaped the entire outer solar system. Neptune may have moved outward by billions of miles. During this chaos, smaller bodies were tossed around constantly. Some were flung into the Sunday, some were thrown into deep space, some were captured into stable orbits like Sedna's, and some, the theory goes, were full-sized planets that simply got ejected. A planet the size of Neptune or even larger could have formed in the early solar system and then been thrown out by a close encounter with Jupiter or Saturn. The math works. Simulations of the early solar system routinely produce scenarios where one or more extra ice giants get kicked out before things settle down. If this happened, the ejected planet would now be a rogue, drifting through interstellar space, possibly hundreds of light years from the Sunday. We could never find it. We could never recover it. It would be lost to us forever. But the orbits it shaped before its departure would survive. Sedna's orbit takes 10,000 years to complete. Ammonite's takes more than 4,000 years. Once the planet was gone, the gravitational scattering processes that maintain orbits stopped acting on them. They froze in place. They became museums of the early solar system, preserving the configurations they had when the architect left. This is what Dr. Yukun Huang suggested when Ammonite was discovered. It is possible that a planet once existed in the solar system, but was later ejected, causing the unusual orbits we see today. If this is correct, the searches for Planet 9 and Planet Y are searching for ghosts. The planets we are hunting for are not here anymore. They have not been here for billions of years. But this theory has a problem of its own. It cannot explain the active warp in the Kuiper belt beyond 80 AU. Remember, Chapter 4. Siraj's team showed that the warp should have decayed long ago if the cause was gone. The warp is fresh. It is being maintained. A ghost planet cannot maintain a gravitational signal that requires active presence. So, the ejection theory works beautifully for the ancient stable orbits of the sednoids, but fails for the recent dynamic warp Siraj discovered, which suggests that maybe the answer is not one theory but 2. Maybe a planet was ejected long ago, leaving the sednoids on their detached paths. And maybe a different planet, Planet Y, is still here, actively warping the closer regions of the belt. 2 events, 2 planets, one still present, one long gone. Picture a stage after a play. The actors have left, the lights are dim, but the chairs are still arranged the way they were placed during the final scene. You can tell that something happened here, even though no one is performing now. The outer solar system might be that stage. The sednoids are the chairs. The audience is missing, and whoever moved the furniture exited long ago. Now imagine that some of the actors did not leave. One stayed behind, moving silently in the wings, still rearranging things in the present. That is the picture some astronomers are forming. An ancient drama, partially over, with one performer still on stage. And the most likely suspect for the ejection? The same gas giants that still anchor our solar system today. Jupiter and Saturn were ruthless landlords. They threw out plenty of tenants. One of those tenants may have been a planet that almost became part of our family. In the chaos of the early solar system, Jupiter and Saturn ruled with iron gravity. Within the first few 100 million years after the Sun ignited, these two giants were the dominant gravitational forces in the outer solar system. Together, they held about 90% of the mass outside the Sunday. Their combined pull controlled the orbits of everything else. Smaller bodies that came too close were flung outward, hurled inward, or destroyed in collisions. This is the violent backdrop against which the ejection theory plays out. Computer simulations of solar system formation routinely produce a scenario known as the Nice model, named after the city in France where it was developed. In this model, the giant planets started in a tighter, more compact configuration than they have today. Over time, gravitational interactions with the surrounding disk of icy debris caused them to migrate. Jupiter moved slightly inward. Saturn, Uranus, and Neptune all moved outward. During this migration, the orbits of the giants crossed certain mathematical resonances. When that happened, the entire system became unstable. Orbits became chaotic. Smaller bodies were scattered everywhere. Some were ejected from the solar system entirely, and in some simulations, an extraplanet was present. Astronomers have run thousands of simulations of the early solar system. Many of them produce a stable final configuration matching what we see today, but only if there were originally 5 or even 6 giant planets, not 4. The extraplanet, often an ice giant similar in size to Uranus or Neptune, would have been thrown out by Jupiter or Saturn during the period of instability. This idea has been around for over a decade. It explains certain features of the solar system that the standard 4-planet model struggles with, including the slightly eccentric orbits of Jupiter and Saturn, the precise distribution of the Kuiper belt, and the existence of the scattered disk of icy bodies beyond Neptune. The extraplanet is sometimes called the 5th giant. It is purely hypothetical, but its existence is consistent with the data. If it was real, it spent perhaps tens of millions of years orbiting the young sun before being ejected. During that time, its gravity reached into the surrounding debris disk and reshaped everything within range. When it was finally thrown out, it left a fingerprint. The orbits of the most distant Kuiper belt objects would have been frozen in the state they were in at the moment the planet left. The sednoids and other detached worlds may all owe their existence to this lost giant. Now imagine what the early solar system would have looked like. 5 gas giants visible in the sky from any planet in the inner regions. A more crowded, more chaotic outer system. Resonances and gravitational waves rippling through the debris. Then, over the course of a few 100,000 years, the chaos resolves. One of the giants is gone. The remaining 4 settle into the orbits we know today. The ejected planet would now be a rogue, wandering through the galaxy, maybe captured by another star, maybe still drifting. We have no way to find it. There are billions of rogue planets in the Milky Way, and identifying any one of them as a former member of our solar system is currently impossible. But the implications matter. Every time astronomers find another solar system with strange features, they wonder if those features come from ancient ejections. The discovery that ours may have lost a planet in its youth suggests that planet loss is a normal part of how solar systems mature. Picture a young family in a crowded apartment. There were too many siblings for the space. Eventually, one of them had to leave. The remaining siblings grew up with stories about the missing one, the empty room, the toys that were not used, the space at the dinner table. Our solar system might be that family. The empty space in the outer regions might be the bedroom that used to belong to a brother who left. This is one of the most beautiful and haunting ideas in modern planetary science. The notion that our cosmic neighborhood is not just complex, but is the survivor of an even more complex past. And speaking of survivors, there is one more category of evidence we have to consider. Not planets that left, not planets that are still here, but stars. Stars that came close enough to the early sun to leave their own marks on the Kuiper belt. Stars that passed by, dropped their gravitational stones into the lake, and continued on their way. The sun is moving, so is every other star in the galaxy. We orbit the center of the Milky Way at about 500,000 miles per hour, completing one full circuit every 230 million years. This means that the stars near us are constantly changing positions. Over millions of years, individual stars drift closer to or farther from the sun they most pass at safe distances. Occasionally, one comes close enough to disturb our solar system. This is the second major hypothesis for what shaped the outer Kuiper belt, a passing star. Astronomers have already identified several stellar visitors from our distant past. The most famous is Scholz star, a small red dwarf that came within about a light year of the Sun roughly 70,000 years ago. That is closer than any star is right now. Its passage was probably brief, lasting only a few thousand years from approach to retreat. But during that time, its gravity may have stirred up the Oort cloud and sent comets tumbling toward the inner solar system. If a closer or larger star ever passed by, the effects would have been much more dramatic. We consider a close stellar flyby as an explanation for the abrupt termination of the classical Edgeworth-Kuiper belt at around 50 AU from the Sun, and also for the high values of orbital excitation observed. A star skimming through the outer solar system, perhaps at a distance of 150 or 200 astronomical units, could have done enormous damage. It could have stripped away material beyond the cliff, creating the abrupt outer edge of the Kuiper belt. It could have flung individual objects onto extreme elongated orbits, possibly creating the sednoids. It could have torn away part of the original protoplanetary disk and left the solar system with a hard rim. This idea has appeal because it does not require any hidden planets. It explains the cliff, it explains the detached worlds, and it leaves no evidence of a current intruder. The star is long gone, having continued on its journey through the galaxy. But there are problems. A stellar flyby is essentially a one-time event. Whatever it did during the few thousand years of its closest approach. After that, the gravitational disturbance starts to decay. Over billions of years, the orbits of objects in the disturbed region should slowly relax back toward their natural configuration. This is what Siraj and his team tested when they ruled out a stellar flyby as the cause of the 15-degree warp. A flyby produces a temporary signal that fades. The warp we see today should have faded long ago if a passing star was the cause. So the flyby cannot explain the active warp. It might still explain the cliff, since the cliff is essentially a missing population of objects. Once material is stripped away, it stays stripped. It does not come back. The flyby could have permanently removed everything beyond a certain distance, and that gap would persist forever. The flyby might also explain the sednoids. Their orbits, while stable for billions of years, were established long ago. A passing star 4 billion years ago could have flung Sedna outward, and the orbit would still be visible today. The detached worlds are old fingerprints, not fresh ones. Astronomers are now trying to figure out whether the early sun did pass through a denser stellar environment that would have made close encounters more likely. Picture a young child standing in a crowded playground. Other children rush past, occasionally bumping into them. As the child grows older and moves to a quieter neighborhood, the bumps stop. The fingerprints from those early collisions, though, can still be detected on the child's clothes. Our sun was born in a stellar nursery. Hundreds, possibly thousands of newborn stars, all packed into a region a few light years across. Close encounters in this environment would have been common, perhaps inevitable. Some of the strange features of the outer solar system may date back to that crowded infancy. imprints from passing siblings set down before any planet was fully formed. That nursery is gone now. The Sun has long since drifted free of its birth siblings, scattered into different orbits around the galaxy. Our brothers and sisters are now strangers, indistinguishable from any other stars. But somewhere out there, one of them may have left a mark we can still read. And the mark might be the very thing pulling on the Kuiper belt today. Every star in the galaxy was born in a nursery. The Sun is no exception. About 4.5 billion years ago, a cloud of gas and dust collapsed and gave birth to thousands of stars almost simultaneously. The cloud was a stellar nursery, and the Sun was one of perhaps several thousand siblings born within it. These stars did not stay together. Over hundreds of millions of years, gravitational interactions with the rest of the galaxy slowly pulled the cluster apart. By the time Earth had cooled enough to host liquid water, the Sun was already drifting away from its siblings. Today, those original cluster members are spread across thousands of light years of the Milky Way, indistinguishable from any other stars. But during the first few 100 million years of its life, the Sun was surrounded by other newborn stars. Some of them passed close, some of them shared gravitational interactions, and some of them may have left objects behind. This is where the story gets interesting. When two young stars pass close to each other, gravitational tides can transfer material between them. Comets, planetesimals, even planets can be exchanged. A planet originally orbiting one star can be captured by the other, becoming a permanent member of a system it did not originally belong to. This is one of the proposed origins for Planet 9. If a planet was captured during the Sun's time in its birth cluster, the capture would have happened billions of years ago. The captured planet would have spent the rest of solar system history settling into a stable orbit. Today, it would be virtually indistinguishable from a native planet, except for its tilted, eccentric orbit and its alien chemistry. The sednoids may also be products of cluster encounters. Researchers have shown that close stellar passes during the cluster era could have lifted the perihelia of certain Kuiper belt objects to the levels we see in Sedna and its cousins. The objects would have been on normal orbits, then nudged by gravitational interaction with a passing star, then frozen in their detached configurations once the Sun left the cluster. This is an attractive theory because it places the strange orbits in their historical context. The early solar system was not a quiet, isolated place. It was crowded, dynamic, and full of close encounters. Many of its peculiarities may date back to that turbulent infancy, but the theory has the same problem as the simple flyby hypothesis. It cannot explain the active warp Siraj found. Whatever the cluster did, it did long ago. The warp must have a current source. This is why most astronomers now believe the outer solar system has multiple stories layered on top of each other. The Kuiper cliff might be due to a flyby or a cluster encounter. The sednoids might be the work of a captured planet or a close stellar pass. The active warp must be due to a planet still in residence. Picture an old house with several owners over its history. Each one made changes. One built an addition, one painted the walls, one installed a fountain in the yard. By the time you walk through it, the house bears the marks of every previous resident. You can trace each layer of change to a different time and a different person. The outer solar system might be that house. The marks we see today were not all made by the same hand. Some are ancient, some are recent, some are still being added, and one of the residents may still be living there, walking the halls in the dark, leaving footprints we are only now starting to recognize. The strangest thing about the cluster era is what it implies about other star systems. If our Sun exchanged planets with its siblings, then other planetary systems likely did too. Some of the worlds we see around other stars may have been born around different ones. The galaxy is more interconnected than we used to think. Stars share their children, their planets, their material, all in a long-forgotten cosmic adoption process. We will probably never know which siblings the Sun spent its youth with. They are too far gone, too thoroughly mixed into the general stellar population. but we may be able to identify their legacy. The hidden planet, if it exists, may be a relic of those forgotten neighbors, a child of one star raised by another. Stop for a moment and imagine standing on Planet 9. If the original estimates from Batygin and Brown are correct, you would be on a world about 5 to 10 times the mass of Earth and roughly 2 to 4 times its diameter. The gravity at the surface would depend on the exact size, but for a typical estimate, you would weigh somewhere between 1.5 and 2 times what you weigh on Earth. The surface would be locked in eternal twilight. Even at the planet's closest approach to the Sun, sunlight would be more than 100,000 times weaker than what reaches Earth. The Sun in your sky would be the brightest star, easily the most prominent object in the heavens, but not bright enough to call it day. It would look like a brilliant point of light, slightly larger than Venus appears from Earth, casting only the faintest of shadows. At the planet's farthest distance from the Sun, possibly 800 AU or more, the Sun would dim to the point where it would barely outshine the brightest stars. From there, the cosmos would look almost as it does from interstellar space. A year on Planet 9 would last between 10,000 and 20,000 Earth years. It was predicted this thing would be 10 times the mass of the Earth and orbiting so far from the Sun that it would take somewhere between 10,000 and 20,000 years to complete a single orbit. These numbers would later be refined to 6 times Earth's mass in a roughly 7,400-year orbit. Think about what that means. The last time Planet 9 was in its current position in its orbit, humans had not yet invented writing. The next time it returns to where it is right now, the descendants of our descendants will be looking up at it. Civilizations rise and fall in less time than a single year on this world. The surface would be frozen solid, temperatures of minus 370 degrees Fahrenheit or colder. Any water would be harder than steel. Any methane or nitrogen, the substances that on Earth are gases, would be ices. The atmosphere, if any, would be thin and made of the most volatile compounds, perhaps a faint mixture of hydrogen and helium captured during the planet's formation. If you could stand on the surface, you would see a landscape unlike anything on Earth. The ground might be cracked and ancient, marked by impacts from billions of years of comets and ice fragments. The horizon would extend slightly farther than on Earth, given the larger size of the planet. Above you, the Milky Way would stretch in a way that has not been visible to humans for thousands of generations, because Planet 9 sits well above the level of light pollution and atmospheric scattering that obscures the sky from Earth. The sky itself would be an inky black, deeper than any night sky on Earth, because the atmosphere would be too thin to scatter starlight. You would see millions of stars, far more than the eye can usually detect, all crisp and sharp. And here is the surreal part. From Planet 9, you could see all the inner planets clustered around the Sunday. Earth, Mars, Jupiter, Saturn, all of them would appear as faint points of light near the brilliant central spark of the Sunday. Our entire civilization, all of human history, all the music and wars and discoveries we have ever made would be invisible to the naked eye. We would not even register. A visitor standing on Planet 9 would not know we existed. They would have to look very carefully, with very good instruments, to detect the tiny radio whisper of Earth's transmissions, or the faint thermal signature of our cities. This is the loneliness of the outer solar system. Planet 9, if it exists, has been alone in the dark for the entire age of the Sunday, while Earth has been spinning through its rapid years and hosting the rise and fall of dinosaurs and humans. Planet 9 has barely moved. It has watched the same patch of sky for thousands of generations. It has waited, and now, after 4.5 billion years of obscurity, it is on the verge of being found. Sometime in the next decade, a telescope on Earth will capture the faint glimmer of its surface or the dim warmth of its atmosphere. That moment will be one of the most significant in the history of astronomy. A new planet, named, mapped, and added to the textbooks. The first new world to join our family in nearly 2 centuries. But for now, it remains hidden. And the question of why it has stayed hidden for so long is itself a puzzle worth understanding. a decade of searching, the most powerful telescopes ever built, billions of dollars in observational time, and Planet 9 is still missing. Why? The first reason is brightness. A planet at 400 AU receives only 1/160,000th the sunlight that Earth does. The reflected light it sends back is even weaker. By the time that light reaches Earth, it has traveled a total of about 1,000 astronomical units. Most of the photons are lost along the way. For a Neptune-sized object at this distance, the apparent magnitude would be around 22. For a smaller body, it would be even fainter. Only the largest telescopes can see objects this dim, and even they need long exposures to bring out the signal. The second reason is motion. Planet 9 moves slowly, so slowly that detecting its motion against the background stars requires observations spread over months or years. A planet at 400 AU moves about half a degree per century. That is roughly the diameter of the full moon. Each year, it shifts by only a tiny fraction of that. Most surveys that look for moving objects in the sky are tuned to catch faster movers, like asteroids and Kuiper belt objects. The very slow movement of Planet 9 makes it easy to miss. The third reason is location. The exact position of Planet 9 in the sky depends on its orbital parameters, which are uncertain. Even with the best models, the predicted location covers a strip of sky thousands of square degrees in area. Searching that much sky thoroughly is enormously expensive in telescope time. And here is the cruelest factor. Planet 9 is most likely currently near its farthest distance from the Sun. That is where it spends the most time. Statistically, the planet is more likely to be close to its aphelion at a distance greater than 600 AU. This is because objects move more slowly when near their aphelion, in accordance with Kepler's second law. The farther a planet is from the Sun, the more time it spends moving slowly through that distant region. Like a child on a swing, it lingers at the top of its arc and zips quickly through the bottom. Planet 9, if it exists, is probably right now lingering at the top of its arc, which means it is at the farthest, dimmest, hardest to detect part of its orbit. If we are unlucky, we might have caught it during the worst possible decade for finding it. If we are luckier, it might be moving through a region of sky that surveys have not yet covered carefully. There is also the possibility of obscuration. Some predicted orbits for Planet 9 bring it close to the plane of the Milky Way, where the dense star fields make it almost impossible to pick out a faint, slow-moving point of light. Searching for a planet against the background of the galactic plane is like searching for a particular grain of sand on a beach. The signal exists, but the noise is overwhelming. And then there is the question of what we are looking for. Planet 9 is hypothetical. Its mass, distance, and orbit are all estimated, not measured. If the real Planet 9 is somewhat different from the predictions, current searches may be tuned to miss it. Maybe it is smaller, maybe it is farther. Maybe it has an atmosphere that reflects differently than expected. All of these factors combine to make finding Planet 9 one of the hardest direct detection problems in modern astronomy. It is not impossible, but it requires patience, precision, and luck. The good news is that the tools are now finally up to the job. The Vera Rubin Observatory will scan the southern sky every few nights for a decade. Its sensitivity reaches to magnitude 24, well below where Planet 9 should be. Its software is designed to flag slow-moving objects automatically, and it will search areas that previous surveys never reached. Even if Planet 9 is at its farthest distance, Rubin should be able to detect it within the first few years of the survey. The decade of failure is about to end. The infrared searches, like the Akari analysis we discussed earlier, are also accelerating. New space-based observatories with infrared capability are being designed. Some of them, if launched in the late 2020s, would be optimized for exactly this kind of search. Picture a magician who has been holding a card behind their back for 10 years. The audience has grown impatient. They have squinted, leaned forward, asked questions, demanded answers, Now, finally, the magician is about to turn around. We are about to see what is in their hand, but the search has limits even with all this new technology. There are regions of sky that are genuinely difficult. There are mass ranges where the planet would simply be too dim. And there is one more wrinkle. The hidden planet might already have been photographed, sitting in some old archive, waiting for someone to recognize what they are looking at. Astronomers do not search the sky randomly. They search where the math tells them to look. For Planet 9, the math points to a specific strip of the sky. The orbit that Batygin and Brown originally proposed places the planet most likely in the direction of the constellation Orion, on the far side of the galactic plane from the Sunday. Other models extend the search to nearby constellations like Cetus and Eridanus. The size of the search area is roughly 2,000 to 3,000 square degrees. That is a lot of sky. For comparison, the full moon covers about 1/4 of a square degree. Imagine searching an area equivalent to 10,000 full moons, looking for a single faint point of light. But the math also narrows it. Some regions of the predicted area can be ruled out by previous surveys. The Wide Field Infrared Survey Explorer, known as WISE, photographed the entire sky in infrared light during the 2010s. Subsequent analyses of WISE data have ruled out a Jupiter mass object out to 26,000 AU and a Saturn mass object out to 10,000 AU. So whatever Planet 9 is, it is not as massive as those gas giants. It is likely smaller, in the range of 5 to 10 Earth masses, exactly as the Kuiper belt clustering suggests. The Pan-STARRS survey, based in Hawaii, has also ruled out brighter and closer versions of Planet 9. Combined with WISE, these surveys have eliminated the easy possibilities. Whatever is out there, it has stayed hidden by being smaller, fainter, or farther than the previous searches could reach. For Planet Y, the search regions are different. Because Planet Y is closer, between 100 and 200 AU, it would move faster across the sky than Planet 9. Each year, Planet Y would shift its position by a measurable amount. This makes it potentially easier to detect through motion-based searches, but harder to detect through static surveys. The predicted tilt of Planet Y, at least 10 degrees from the planetary plane, also affects where to look. A tilted orbit takes the planet above and below the standard zone where most other planets live. Searches that focus only on the ecliptic, the band of sky where the known planets reside, would miss it. This is one of the reasons Planet Y has remained hidden. Most planet searches have been concentrated on the planetary plane. The regions slightly above and below have received less attention. A planet inclined 10 degrees or more spends most of its time outside the most heavily searched zones. The good news is that the Vera Rubin Observatory does not have these blind spots. Its survey will photograph the entire southern sky uniformly, every few nights, for a decade. There will be no regions of sky left unexplored. Whatever is out there, within the survey's sensitivity, will eventually be catalogued. The catalogue itself is the key. Rubin will produce a database of every object that moves in the sky over its survey period. Algorithms will sift through trillions of data points, looking for the specific signatures of distant solar system objects. A faint smudge of light, moving in a predictable orbit, at the right speed and angle, will be flagged for human review. If Planet 9 is in the southern sky and within Rubin's detection limits, it will appear in this catalogue. The same applies to Planet Y. Even if the planet is not directly imaged in any single exposure, the cumulative search across multiple exposures over multiple years should accumulate enough signal to pull it out of the noise. Mike Brown himself has said that he believes the question of Planet 9 will be settled within 10 years, one way or the other. Either it will be found and named, or it will be ruled out so thoroughly that the hypothesis will be retired. This is a high-stakes moment. For an entire decade, Planet 9 has been an open question, the most famous unsolved problem in solar system astronomy. The mystery that drew Caltech's best minds, generated dozens of papers, and inspired countless news articles. The resolution of the mystery is now within reach. Picture a chess game that has been paused for years, pieces frozen on the board. The next move has been waiting for the right tool to make it. That tool has now arrived. The game is about to restart, and the outcome could change our textbooks forever. But before we get to the conclusion, there is one more piece of evidence to consider. A strange little anomaly from decades ago, involving two old spacecraft that left Earth in the 1970s and never came home. The Pioneer probes felt something out there. In 1972 and 1973, NASA launched two spacecraft into the outer solar system, Pioneer 10 and Pioneer 11. They were the first human-made objects to cross the asteroid belt, fly by Jupiter, and head out toward the stars. Both probes carried a small gold plaque depicting a man, a woman, and the location of Earth in the galaxy. The message was a greeting to any civilization that might find the spacecraft millions of years from now. But before they became interstellar messengers, the Pioneers gave us something unexpected. As they sailed past the orbit of Uranus and beyond, NASA tracked their positions with extraordinary precision. The Doppler shift of their radio signals could be measured down to fractions of a millimeter per second. Year by year, scientists compared the actual positions of the probes to where they should be based on the gravitational pull of the Sun and the planets. The two numbers did not match. When these probes were still within the solar system, at 20 AU, that is, between Uranus, which has a mean distance from the Sun of 19.13 AU, and Neptune, at 30 AU, the frequency received at Earth starts showing an unaccounted effect, a blue shift that is usually interpreted as a constant acceleration with a magnitude of approximately 8.74 times 10 to the negative 8 centimeters per second squared, directed towards the Sunday. The probes were experiencing a tiny extra pull toward the Sunday, so small you would not notice it on Earth, but measurable in the extreme cold of the outer solar system, over years of careful tracking. This is what became known as the Pioneer anomaly. For decades, scientists puzzled over its cause. Was it gravity from an unseen object in the outer solar system? A primordial black hole? An undiscovered planet? Was it a flaw in our understanding of gravity itself, possibly evidence for theories like MOND? Or was it something more mundane, like heat radiating unevenly from the spacecraft's plutonium power sources? In 2012, a careful reanalysis suggested that the anomaly could be explained by thermal radiation from the spacecraft itself. The probes generated heat, and that heat radiated out preferentially in certain directions due to their design. The asymmetric thermal emission created a tiny thrust toward the Sun, exactly what the data showed. Most scientists now accept this explanation. The Pioneer anomaly, by mainstream consensus, is not evidence for hidden planets. It is a quirk of spacecraft engineering, but not everyone is convinced. Some researchers have argued that the thermal explanation is incomplete. They point out that the residual anomaly, after thermal effects are subtracted, may still be consistent with a tiny extra gravitational pull from outer solar system material. The Kuiper belt itself, with all its accumulated icy bodies, exerts a small gravitational attraction on anything passing through it. Some calculations suggest this could account for part of the unexplained motion. If a planet mass object exists in the outer solar system, it would also contribute. A planet 9 or planet Y at the right location could subtly bias the motion of distant spacecraft. The effect would be tiny but not zero. The Pioneer probes are no longer in contact with Earth. Pioneer 10 last communicated in 2003. Pioneer 11 went silent in 1995. But Voyager 1 and Voyager 2 are still active, and they are continuing to travel into the outer solar system. NASA is monitoring their motion carefully. If a hidden gravitational source exists, the Voyagers may eventually detect it. There is also the New Horizons spacecraft, which flew past Pluto in 2015 and is now deep in the Kuiper belt. New Horizons is being used to refine the masses of distant Kuiper belt objects and to test the gravity of the outer solar system. Any unexplained acceleration in its motion could provide additional evidence for hidden mass. The Pioneer anomaly story is a reminder that the outer solar system has been surprising us for decades. Even the most careful measurements turn up unexpected effects. Even the most mainstream explanations have lingering doubts. The dark, cold edge of our solar system continues to defy easy understanding. Picture two old explorers trudging into a frozen wilderness. They send back letters describing what they see. Most of the letters can be explained by ordinary observations, but occasionally there is a sentence that does not quite fit, a description of an unfamiliar shape on the horizon, glimpsed through fog. The explorers cannot say what it is. They can only say it is there. The Pioneer anomaly is one of those sentences. Probably nothing, possibly something, a whisper from the dark. And if Planet 9 or Planet Y is real, the Voyagers may eventually whisper the same thing. We will be listening. The Vera Rubin Observatory will start its serious sky mapping work in 2026. Within 5 years, it should have collected enough data to definitively answer the question of Planet 9 and Planet Y. But what if the answer is no? What if Rubin completes its survey, the algorithms run, the data is analyzed, and no hidden planet is found? This is a real possibility. The Kuiper belt anomalies might not be caused by hidden planets at all. They might be caused by selection bias, statistical fluctuations, or processes we have not yet imagined. The case for Planet 9 and Planet Y rests on indirect evidence. Indirect evidence can be misleading. If Rubin finds nothing, several things would happen. First, the Planet 9 hypothesis would be largely retired. Some die-hard supporters would argue that the planet is even farther out than expected, beyond Rubin's reach. But most astronomers would conclude that the original interpretation of the orbital clustering was wrong. Second, the alternative explanations would gain ground. MOND might receive serious, renewed attention. The idea that gravity behaves differently at very low accelerations would suddenly become harder to dismiss. New tests of modified gravity would be designed. Theorists would have a fresh playground. Third, the ancient ejection hypothesis would become the leading explanation for the sednoids. If no current planet exists in the predicted regions, then the orbits of the detached worlds must have been set up by something that is no longer here. The ejected fifth giant would become the most popular candidate, and theorists would work to figure out exactly when and how it left. Fourth, the Kuiper cliff would remain unsolved. Without a hidden planet to explain its sharp edge, the cliff would join the list of long-standing solar system mysteries. New theories would emerge, old ones would be revisited, and fifth, attention might shift to even more distant searches. The Oort cloud, the spherical shell of comets that extends from a few thousand AU out to a light year or more from the Sun, contains an estimated trillion objects. The Sun's gravity weakens to almost nothing at these distances. Anything significant out there is virtually undetectable with current technology. A planet at 3,000 or 5,000 AU is not impossible. It would be far harder to find than even Planet 9. But the absence of evidence at 400 AU would push the search outward. The negative result would not be a failure for science. It would be a clarifying success. Knowing what is not there is as important as knowing what is. Every theory that fails leads to better theories. Every search that comes up empty narrows the space of possibilities and forces astronomers to think harder. There is also the possibility that Rubin finds something unexpected. Not Planet 9, not Planet Y, but something else entirely. A new class of objects we have not yet imagined. A new structural feature of the Kuiper belt. A new resonance, a new family, a new cluster. The outer solar system has surprised us many times. It surprised us with Pluto in 1930. It surprised us with the Kuiper belt itself, predicted in the 1950s but not confirmed until 1992. It surprised us with Sedna in 2003. With each new survey, the outer solar system has revealed something its discoverers did not expect. Rubin will almost certainly continue this trend. Whether or not Planet 9 is found, the survey will produce discoveries that change our picture of the outer solar system: new dwarf planets, new trans-Neptunian families, new evidence of how the planets formed and migrated. This is the nature of large surveys. They cast wide nets, and the unexpected catches are often the most valuable. Picture a detective who has been hunting one suspect for a decade. They finally execute the warrant on the suspect's hideout. The suspect is not there, but the hideout contains evidence of an entirely different crime committed by a different person that no one had been looking for. That is what Rubin might give us. Not the answer we expect, but a better question we did not know to ask. And here is the deeper truth. Even if the hidden planet hypothesis is wrong, the patterns in the Kuiper belt are real. Something is causing them. The warp, the alignment, the cliff, these are all measured features of our solar system. If not planets, then what? Finding out is the entire point of doing science. One of the most respected astronomers in the field has put a date on the answer: observation and analysis of the orbital dynamics of Kuiper belt objects constrain the possible orbital parameters of a planet 9. And at the current rate of new observations, University of Michigan professor Fred Adams believes enough data will have been gathered to pinpoint Planet 9 or rule out its existence by 2035. 2035. 9 years from now. By that point, the Vera Rubin Observatory will have completed most of its 10-year survey. The catalogue of known trans-Neptunian objects will have grown from a few thousand to tens of thousands. The statistical signature of any hidden planet, if present, will have either emerged clearly or vanished entirely. This is a specific, falsifiable, near-term deadline. It is not the vague timeline of most astronomical questions, where answers may take a century. It is concrete, it is fast, and it is happening within the working careers of the scientists who proposed the hypothesis. For Mike Brown and Konstantin Batygin, the original proposers of Planet 9, this is the endgame. They have spent a decade defending and refining their hypothesis. They have absorbed criticism, adjusted their models, and watched their predictions either confirm or fail. By 2035, they will know. For Amir Siraj and the Planet Y team, the timeline is similar. Their hypothesis is younger, only formally proposed in 2025. But the same flood of data from Rubin will resolve it. A Mercury to Earth mass planet at 150 AU should be even easier to detect than Planet 9, because it is closer and brighter. By 2035, we should have answers to at least 3 major questions. Does Planet 9 exist? Does Planet Y exist? Are the orbital anomalies in the Kuiper belt caused by hidden planets, by modified gravity, by ancient ejections, or by some combination? If even one of these planets is found, the consequences will be enormous. The solar system will have a new member, textbooks will be rewritten, probes will be designed to study the new world. The discovery will dominate scientific news for years. If neither is found, the consequences will be just as profound. The leading hypotheses of the last decade will be retired. New ideas will take center stage, possibly Mond, possibly more exotic theories. The mystery will not be solved, but it will be reshaped. There is also a third possibility, something unexpected, a different planet, a different number of planets, a completely new explanation that no one has yet considered. The history of astronomy is full of these surprises. The Kuiper belt itself was such a surprise, predicted but not appreciated until the discoveries began rolling in. The 2035 deadline is not just for the planet question, it is for our entire understanding of the outer solar system. By that date, we will know much more about how the icy worlds beyond Neptune are organized, how they move, and what they tell us about the early history of our planetary neighborhood. This is a special time to be alive for astronomy. The combination of new telescopes, new computing power, and new theoretical insight is creating an unprecedented opportunity. Questions that have lingered for decades are about to be answered. Mysteries that have inspired generations of researchers are approaching resolution. It is hard to overstate how rare this moment is. Most scientific questions take a long time to resolve. Most theories age slowly. Most data accumulates incrementally over decades. But the Planet 9 question, partly because of the firm theoretical predictions, and partly because of the specific capabilities of the Rubin Observatory, has a sharp endpoint. In 9 years, the question will not be open anymore. Picture a long, ambling road trip that has been going on for a decade. The destination has been a rumor, a hope, a guess. Now, finally, you are pulling into the final stretch. The signs are clear. The arrival is imminent. The view is about to open up. That is where Planet 9 science stands. The final stretch is here. The arrival is close. And whatever we find, or do not find, will change how we think about our home in the universe. The history of the solar system has been rewritten before. In 1930, an American astronomer named Clyde Tombaugh discovered Pluto. For 76 years, Pluto was the 9th planet. Generations of children learned the planets in order, with Pluto as the final, faint, frozen member of the family. Then, in 2006, the International Astronomical Union redefined the term planet. Pluto did not fit the new definition. It was demoted to dwarf planet. Textbooks were rewritten. Children stopped learning about 9 planets and started learning about 8. The discovery of a new planet, if it happens, would reverse that direction. We would go from 8 planets to 9, or even to 10, if both Planet 9 and Planet Y turn out to be real. The new planet would not be like Pluto. It would not be a dwarf. It would be a full-fledged member of the solar system, with enough mass and gravitational dominance to qualify as a planet by the modern definition. Brown notes that the putative 9th planet, at 5,000 times the mass of Pluto, is sufficiently large that there should be no debate about whether it is a true planet. Unlike the class of smaller objects now known as dwarf planets, Planet 9 gravitationally dominates its neighborhood of the solar system. If Planet 9 is found, it would be the first new major planet added to the solar system since the discovery of Neptune in 1846. That is 180 years between major planetary discoveries. An entire scientific era between the addition of new members to our planetary family. The implications would extend well beyond astronomy. School children would learn 9 planets again, or 10 if Planet Y is also confirmed. The names of the planets would change. The poems and mnemonics that students use to memorize them would have to be updated. A century of textbook tradition would be revised. The science would also explode. A new planet means new questions. How did it form? What is it made of? Does it have moons? Does it have an atmosphere? What can it teach us about how planets form and evolve in general? Within a few years of confirmation, space agencies around the world would begin designing missions to study the new planet. The technical challenges are enormous. A probe sent to Planet 9 would take decades to arrive. The Voyager spacecraft, which left Earth in 1977, have only just reached the distance where Planet 9 is believed to be. Any new mission would need significantly faster propulsion or longer mission timelines. But the science would justify the effort. A flyby of an undiscovered planet, even a brief one, would yield more new knowledge per dollar than perhaps any other space mission in history. The information about how the outer solar system formed, what kinds of objects exist in cold, deep space, and what conditions are like at the edge of our gravitational neighborhood would be worth the wait. There is also a cultural dimension. A new planet changes how we see ourselves. The 8-planet solar system feels small and finite. Adding a 9th or 10th member expands our sense of cosmic neighborhood. It reminds us that even the place we live, the system we have inhabited for our entire existence, can still surprise us. For 400 years, since Galileo first turned a telescope on the moon, humans have been mapping our cosmic backyard. We have charted the planets, the moons, the asteroid belts, the comets, the dust. We thought we knew where everything was. We were wrong, and the discovery would change something deeper. It would prove that the outer solar system is not a finished story. There are still hidden things out there, things big enough to count as planets, things that have been with us since the beginning, sharing the sun's gravity, drifting through the cold for billions of years, waiting for us to notice them. If Planet 9 and Planet Y both exist, the implications grow. Two hidden giants in our own backyard. How many more might there be? Where else have we been blind? What else are we missing? These are not small questions. They are foundational. They go to the heart of how confident we should be about the universe we think we understand. Picture a long-time resident of a house who has lived there for decades, who knows every room and every corner. One day, they discover a hidden door behind a bookshelf. Behind the door is another room. They had no idea it existed. They have walked past it thousands of times. That is what finding Planet 9 would feel like. A hidden room in the house we thought we knew completely. And there is one more thing to consider. The biggest question of all. The one that ties this entire story to everything beyond the solar system. If our sun has hidden planets, what about the others? There are roughly 400 billion stars in the Milky Way galaxy. Most of them are believed to host planets. Some host hundreds. The galaxy is teeming with worlds we have only just begun to discover. If our own sun, the star we know best, has been hiding planets from us, what does that say about every other star system out there? For the past 30 years, astronomers have been finding exoplanets, planets orbiting other stars at an accelerating pace. As of 2026, more than 5,000 exoplanets are confirmed. Many of them are strange. Some are hot Jupiters, gas giants orbiting closer to their stars than Mercury does to ours. Some are super-Earths, rocky worlds larger than Earth but smaller than Neptune. Some are in orbits so distant they take thousands of years to complete. The methods we use to detect these worlds are biased toward finding planets close to their stars. The closer a planet is, the easier it is to detect through transits, where the planet passes in front of its star and dims its light, or through radial velocity, where the planet's gravity tugs the star toward and away from us. But planets in very wide orbits, like Planet 9 would be, are nearly impossible to detect with these methods. They do not transit often enough. They do not produce strong enough radial velocity signals. They are simply too far from their parent stars to leave clear fingerprints. This means that every star system we have studied could be hiding planets in its outer regions. The catalogues of known exoplanets, despite their size, are dramatically incomplete. We see the inner zones clearly. The outer zones are dark. If Planet 9 is real in our solar system, it would prove that hidden distant planets are at least possible. It would justify investment in new technologies designed to find their counterparts around other stars. Direct imaging missions, like the proposed Habitable Worlds Observatory, could begin specifically targeting the outer regions of nearby star systems, searching for planets that would otherwise be invisible. The implications would extend to our understanding of how solar systems form. Standard models of planet formation work well for close-in planets. They struggle with planets in wide orbits. If hidden distant planets are common, our entire theory of how stars and planets form together may need revision. There is also the question of life. Most discussion of habitable planets focuses on the habitable zone, the narrow band around each star where liquid water can exist. This zone is typically close to the star, but hidden planets in the outer regions of star systems could harbor moons with subsurface oceans, warmed by tidal flexing and internal heat. These moons could potentially host life. In our own solar system, the moons of Jupiter and Saturn already provide proof of concept. Europa has an ocean beneath its icy crust. Enceladus shoots geysers of water into space. Titan has lakes of liquid methane. If similar moons exist around hidden planets in the outer solar systems of other stars, the number of potentially habitable worlds in the galaxy could be much higher than current estimates suggest. This is the deepest implication of the Kuiper Belt mystery. It is not just about our own neighborhood. It is about every neighborhood, about every star and every system, about the structure of planet formation and the distribution of life-bearing worlds across the cosmos. The icy worlds at the edge of our solar system are whispering. We are only beginning to listen carefully, and what they are saying may turn out to be one of the most important messages in the history of astronomy. Picture a long road into a vast forest. We have explored only the trees along the path. The forest extends in every direction, dense and unknown. The trees we have catalogued might tell us about the trees we have not yet seen, but only if we are willing to walk farther. We are walking farther now, every year, every month, every observatory. The Kuiper belt is the first step into that forest. The hidden planets, if they exist, are the first new trees we will find. Beyond them, in the dark beyond, there are countless others, around other stars, in other places, possibly with conditions for life, possibly with stories of their own. The story of what is pulling on the Kuiper belt is not just a local mystery. It is a hint of what is hidden everywhere, a reminder that even our own backyard contains secrets we have not yet uncovered, a promise that the universe is bigger, stranger, and more inhabited than we currently know. Within the next decade, we will know whether Planet 9 and Planet Y are real. Within the next century, we will know whether similar planets are common around other stars. Within the next millennium, we may even know whether some of them harbor life. The Sun has been with us for 4.5 billion years. We have studied it for 400. We are still finding its secrets. The journey is just beginning.